The desert air over Edwards Air Force Base hung still and clear in the pre-dawn darkness of August 27th, 2003. In the hours before sunrise, when the Mojave Desert becomes a cathedral of silence, dozens of engineers, technicians, and scientists made their way through the darkness toward remote locations scattered across the dry lake bed. Their headlights cut through the gloom, illuminating reflective markers on sticks that guided them to their stations. On this particular morning, they had to stop more than once, waiting patiently as desert tortoises slowly crossed the dirt roads, oblivious to the historic moment about to unfold above them. These men and women were participants in something that had been 40 years in the making. They were about to witness the culmination of decades of theoretical work, computational modeling, and pure determination. They were there to answer a question that had plagued aviation since October 14, 1947, when Chuck Yeager first broke the sound barrier in the Bell X-1 over this very same desert. The question was deceptively simple. Could an aircraft fly faster than sound without creating the thunderous boom that had banned supersonic flight over land for more than 3 decades? At precisely 6:26 in the morning, just as the sun began to paint the eastern horizon with streaks of orange and gold, 2 aircraft lifted off from the runway at Air Force Plant 42 in Palmdale, California. The first was a modified F-5E fighter jet, painted in distinctive blue and white pinstripes that represented something far more significant than mere decoration. Those stripes depicted the sonic boom signature this aircraft was designed to create. The second aircraft was a standard Navy F-5E, serving as a baseline for comparison. Both planes climbed rapidly into the crystal-clear morning sky, their twin engines leaving contrails that caught the early light. 20 minutes later, both aircraft had reached 45,000 feet. The modified F-5, nicknamed the Pelican by those who had worked on it, lit its afterburners and began a 12-degree dive toward the supersonic corridor. The pilot, Roy Martin, a veteran test pilot with more than 9,600 hours of flight time, pushed the aircraft through the sound barrier and leveled off at 32,000 feet, maintaining a steady speed of Mach 1.36. The standard F-5E followed 45 seconds behind, flying the exact same profile. Below them, spread across 6 miles of desert floor, 42 sophisticated sensors waited. Some were microphones so sensitive they could detect pressure changes of just 0.003 of a pound per square foot. Others were specially designed systems that measured shock waves more than 8,000 times per second. All of them were aimed at the sky, ready to capture what happened when those 2 sonic booms reached the ground. When the data began flowing into laptop computers at the sensor sites, there was an immediate reaction. Engineers looking at the screens could see it instantly. The modified F-5's sonic boom signature looked nothing like the sharp N-wave pattern that had characterized every supersonic aircraft since the dawn of the jet age. Instead, it showed a flattened top, spreading out the pressure rise over a longer period. The initial pressure spike measured 0.82 pounds per square foot, compared to 1.2 pounds per square foot from the standard F-5E. Even more remarkably, the modified aircraft's boom was noticeably quieter to the human ear. At the Northrop Grumman Control Center back at Plant 42, Ken Plotkin, one of the world's leading sonic boom experts, did a small victory dance when he saw the data. He immediately called Albert George at Cornell University to deliver the news. George, along with Richard Seabass, had developed the theoretical foundation for sonic boom minimization back in 1971. For more than 3 decades, their theory had remained just that, a theory, untested by actual flight. Now, in a span of less than 30 minutes, it had been validated beyond any doubt. Peter Cohen, the NASA program manager who had worked tirelessly to make this demonstration possible, jumped up from his seat at the NASA Dryden control room and announced to everyone present that they had just witnessed a classic flat-top signature. The decades of wind tunnel tests, computational fluid dynamics analyses, design iterations, and bureaucratic negotiations had all led to this moment. An aircraft had flown faster than sound, and the sonic boom reaching the ground was measurably, demonstrably quieter than any that had come before. This achievement represented far more than a successful flight test. It was a proof of concept that could potentially revolutionize air travel. For more than 30 years, supersonic flight over land had been banned in the United States and many other countries because of the disruptive sonic booms created by aircraft like the Concorde. This regulation had effectively killed the supersonic transport industry, confining such aircraft to routes over water. But now, for the first time in history, there was tangible evidence that the sonic boom could be shaped, controlled, and reduced to levels that might one day be acceptable for overland flight. The shaped sonic boom demonstration was the product of an unusual collaboration between the Defense Advanced Research Projects Agency, NASA, Northrop Grumman, and the US Navy. It involved more than 100 scientists, engineers, and support personnel working across multiple facilities over more than 2 years. The aircraft itself had been extensively modified with a new elongated nose section and carefully designed underbody fairings that changed how shock waves formed and propagated through the atmosphere. The modifications were based on cutting-edge computational fluid dynamics that could model airflow and shockwave formation with unprecedented precision. But the story of this breakthrough doesn't begin in August of 2003, nor does it start with DARPA's Quiet Supersonic Platform program in the year 2000. To truly understand the significance of what happened over Edwards Air Force Base that morning, we need to go back much further, to the very origins of supersonic flight and the sonic boom problem that this demonstration finally addressed. We need to understand the physics of shock waves, the history of sonic boom research, the regulatory environment that stifled supersonic aviation, and the decades of theoretical and experimental work that made this breakthrough possible. This is the story of how engineers tamed thunder. It's a story of persistence, innovation, and the refusal to accept that some problems are simply unsolvable. It's a story that begins 56 years earlier, in the same desert, when a young test pilot named Chuck Yeager first pushed through the invisible wall that people once called the sound barrier. The dawn of supersonic flight and the birth of a problem. The history of supersonic flight begins with a mystery and a fear. Throughout the 1930s and early 1940s, pilots pushing high-performance aircraft to their limits encountered what they called compressibility effects. As aircraft approached the speed of sound, which varies with temperature but sits around 760 miles per hour at sea level, strange and often terrifying things began to happen. Control surfaces would lose effectiveness or even reverse their function. Aircraft would shake violently, buffeted by forces the pilots couldn't see. Some planes broke apart in mid-air, killing their pilots. Others fell into uncontrollable dives from which recovery was impossible. The phenomenon became so well known and so feared that aeronautical engineers began speaking of the sound barrier as if it were an actual physical wall. Some theorists even suggested that aircraft would never be able to fly faster than sound, that the laws of physics simply wouldn't allow it. But a few engineers, working with early wind tunnels and theoretical models, began to suspect that the problem wasn't insurmountable. They believed that the violent forces encountered near the speed of sound were simply shock waves, discontinuities in the airflow where pressure, temperature, and density changed almost instantaneously. The trick, they theorized, was to design aircraft that could handle these forces and push through them into the supersonic realm. In 1944, the National Advisory Committee for Aeronautics, the predecessor to NASA, met with representatives from the Navy and Army to discuss the possibility of breaking the sound barrier. The Army initially rejected the idea, but was persuaded to support the effort. A joint program was established to build a rocket-powered research aircraft specifically designed to explore transonic and supersonic flight. Bell Aircraft Corporation won the contract, and by 1946, the first XS-1 experimental aircraft had been built. The XS-1, later renamed the X-1, looked more like a bullet with wings than a conventional aircraft. Its fuselage was shaped after a .50 caliber machine gun round, which engineers knew could fly supersonically without disintegrating. It had thin, straight wings and a powerful rocket engine that burned liquid oxygen and ethanol. Because it couldn't take off under its own power, the X-1 was carried aloft under the belly of a modified B-29 bomber and dropped at altitude, where its pilot would light the rocket engine and climb toward the edge of space. The test program proceeded cautiously through 1946 and 1947. Each flight pushed a little faster, a little higher, gathering data on how the aircraft behaved as it approached the speed of sound. On October 14, 1947, with Captain Charles Chuck Yeager at the controls, the X-1 pushed through Mach 1.0, reaching a speed of approximately 700 miles per hour at an altitude of 45,000 feet over the Mojave Desert. The flight was classified at the time, but when the news eventually became public, it electrified the aviation world. The sound barrier had been broken. Supersonic flight was possible, but with this achievement came an unexpected consequence, one that would eventually become a more significant barrier to supersonic aviation than the physics of transonic flight had ever been. When an object moves through air faster than sound, it creates shock waves that propagate outward in a cone shape. These shock waves are regions where air pressure, density, and temperature change nearly instantaneously. When these waves reach the ground, they create a sharp, explosive sound that we call a sonic boom. The sonic boom from the X-1 that morning was heard across the desert, a double crack like thunder from a clear sky. At the time, it seemed like a minor side effect of a historic achievement. Nobody realized that this acoustic signature would eventually become the single biggest obstacle to commercial supersonic flight. Throughout the 1950s, as the United States and Soviet Union raced to develop faster and more capable military aircraft, sonic booms became increasingly common over populated areas. The Century series fighters, the F-100 Super Sabre, F-101 Voodoo, F-102 Delta Dagger, F-104 Starfighter, F-105 Thunder Chief, and F-106 Delta Dart were all capable of supersonic flight, and they regularly broke the sound barrier during training exercises and test flights. Air Force bases located near cities would generate hundreds of sonic booms per month as pilots practiced high-speed maneuvers. The public's reaction to sonic booms evolved from initial excitement to growing annoyance and eventually to organized resistance. The sharp double bang of a sonic boom could rattle windows, set off car alarms, disturb sleeping children, and in some cases cause minor structural damage to buildings. More importantly, the boom was startling and unnerving, especially for people who didn't understand what caused it. Some communities near Air Force bases reported hundreds of complaints per month. As military jets became larger and flew faster, the sonic booms grew stronger. The larger the aircraft and the faster it flew, the more powerful the shock waves it generated. By the early 1960s, there were documented cases of sonic booms causing building damage, cracking plaster, breaking windows, and creating enough ground vibration to disturb livestock. A famous incident in Oklahoma City, where the Air Force conducted a 6-month study involving 8 sonic booms per day, resulted in significant public backlash and numerous damage claims. The Oklahoma City test, conducted from February to July of 1964, was intended to determine whether people could acclimate to regular sonic booms. The idea was that if commercial supersonic transports were going to fly over populated areas, the public would need to accept sonic booms as a normal part of daily life, much as they had accepted the noise from subsonic jets. 8 times each day, F-104 starfighters and B-58 Hustlers flew supersonic over the city at altitudes ranging from 30,000 to 41,000 feet, generating sonic booms across the metropolitan area. The experiment was a disaster from a public relations standpoint. While some residents did report that they grew accustomed to the booms over time, many others found them increasingly intolerable. The city received thousands of complaints and nearly 1,500 damage claims, totaling over $200,000. More significantly, organized opposition to sonic booms grew dramatically. Citizens formed advocacy groups, newspaper editorials condemned the practice, and political pressure began to mount for restrictions on supersonic flight over populated areas. The Oklahoma City test occurred during a period of intense interest in supersonic commercial aviation. Both the United States and Europe were developing supersonic transports that would revolutionize long-distance air travel. The Anglo-French Concorde, the Soviet Tu-144, and the American Boeing 2707 were all in various stages of development. These aircraft promised to cut transoceanic flight times in half, making it possible to fly from New York to London in under 3 hours, or from Los Angeles to Tokyo in 6 hours instead of 12. But the sonic boom problem threatened to undermine the entire concept. If supersonic transports couldn't fly over land without generating unacceptable booms, their utility would be severely limited. They could only fly supersonic routes over oceans, drastically reducing the number of city pairs they could serve profitably. For the American Supersonic Transport Program, which envisioned transcontinental supersonic service, the sonic boom represented an existential threat. The National Aeronautics and Space Administration, which had been formed in 1958 to succeed NACA, began conducting extensive research into sonic booms during the 1960s. They wanted to understand every aspect of the phenomenon. What exactly was a sonic boom? How did it form? How did it propagate through the atmosphere? What factors influenced its strength? Could it be predicted? Most importantly, could it be reduced or eliminated? NASA researchers conducted hundreds of tests using aircraft ranging from small fighters to the massive XB-70 Valkyrie bomber. They flew specially instrumented chase planes through the shock waves of other aircraft to measure the pressure signatures close to the source. They set up arrays of microphones on the ground to measure how shock waves changed as they propagated through the atmosphere. They launched weather balloons to measure atmospheric conditions that might affect sonic boom propagation. They even conducted tests using a Goodyear blimp to measure sonic booms at various altitudes, trying to understand how the shock waves evolved as they traveled from the aircraft to the ground. What they learned was both illuminating and discouraging. A sonic boom wasn't a single event, but a continuous phenomenon. As long as an aircraft flew supersonic, it continuously generated shock waves that propagated outward in a cone shape. The ground track of this cone, called the boom carpet, could be 30 miles wide for an aircraft flying at 30,000 feet. Everyone within that carpet would hear the boom as it passed over them. The boom's intensity was influenced by numerous factors, including the aircraft's size, weight, speed, altitude, and shape, as well as atmospheric conditions like temperature, pressure, humidity, and wind. The pressure signature of a typical sonic boom, when measured on the ground, showed a characteristic N-wave shape. There would be a sudden sharp increase in pressure as the bow shock from the front of the aircraft arrived, followed by a gradual decrease to below ambient pressure as the expansion waves from the aircraft's midsection passed, and then another sharp increase back to ambient pressure as the tail shock arrived. These two sharp pressure rises created the double boom that people heard. The entire event typically lasted less than a second, but those sharp pressure changes contained a lot of acoustic energy across a broad frequency spectrum, making the boom both loud and startling. NASA's research revealed that sonic booms at ground level typically ranged from 1 to 3 pounds per square foot of overpressure for operational military and commercial aircraft. To put that in perspective, 1 pound per square foot equals 48 pascals, and the threshold for human hearing is 20 micropascals. A sonic boom contains roughly 100 decibels of sound energy, comparable to standing near a jackhammer or being at a rock concert. But unlike those continuous sounds, a sonic boom's energy arrives in a fraction of a second, making it particularly startling. The research also showed that sonic booms could be quite variable. Atmospheric conditions played a huge role in how strong a boom would be when it reached the ground. Temperature inversions near the surface could focus shock waves, creating localized areas where booms were much stronger than expected. These focused booms, sometimes called super booms, could have overpressures 2 to 5 times stronger than the cruise boom, and were particularly likely to cause damage. Turbulence in the lower atmosphere could distort the shockwave signature, sometimes making the boom less sharp but spreading it out over a wider area. By the late 1960s, the accumulating evidence about sonic booms was painting a grim picture for the supersonic transport industry. Public opposition was growing. Damage claims were mounting. Environmental groups were beginning to organize against supersonic aviation. And perhaps most significantly, there seemed to be no easy technological fix. Sonic booms were an inherent consequence of supersonic flight. Every design studied, every configuration tested, generated the same characteristic N-wave signature. In 1971, facing intense public and political pressure, the US Senate voted to cut off funding for the Boeing 2707 supersonic transport program. This decision effectively killed American efforts to develop a commercial supersonic aircraft. The official reasons cited were economic. The program was over budget and behind schedule, but the sonic boom problem was widely acknowledged as a contributing factor. Without the ability to fly supersonic routes over land, the business case for a supersonic transport was questionable at best. The only supersonic transport to achieve commercial service was the Concorde, which began flying in 1976. It was a technological marvel, capable of cruising at Mach 2.0 at 60,000 feet, but it was severely constrained by sonic boom restrictions. Concorde could only fly supersonic over oceans. On transcontinental routes, it had to fly subsonic, negating much of its speed advantage. These restrictions, combined with high operating costs and limited seating capacity, meant that only 20 Concordes were ever built, and the type was retired in 2003 after 27 years of service. On March 5, 1973, the Federal Aviation Administration formally banned civilian supersonic flight over land in the United States. Title 14, Part 91 of the Code of Federal Regulations stated that no person may operate a civil aircraft at a true flight Mach number greater than 1 over land unless specifically authorized by the FAA. Similar restrictions were adopted by most other countries. This regulation effectively ended any near-term prospects for supersonic commercial aviation. For the aviation industry, it represented a fundamental limit on how fast commercial aircraft could fly. For researchers interested in supersonic flight, it presented an enormous challenge. But even as the supersonic transport dream seemed to be dying, a small group of researchers refused to give up. They believed that the sonic boom problem might not be insurmountable. They thought that with the right approach, with clever design and advanced understanding of aerodynamics, it might be possible to create an aircraft that could fly supersonic without generating an unacceptable sonic boom. This belief would drive decades of research and eventually lead to that historic morning in August of 2003. The physics of thunder, understanding the sonic boom. To appreciate the breakthrough represented by the shaped sonic boom demonstration, we need to understand exactly what a sonic boom is and why it happens. The physics involved are complex, but the fundamental concepts are quite elegant. When we truly comprehend what happens when an object moves faster than sound, the achievement of shaping and reducing that boom becomes even more impressive. Sound itself is nothing more than a pressure wave moving through air. When something vibrates, a guitar string for example, it pushes air molecules together and then pulls them apart. These compressions and rarefactions propagate outward at the speed of sound. At sea level and standard temperature, sound travels at approximately 760 miles per hour, though this speed varies with temperature and altitude. At the cruising altitude of most commercial jets, around 35,000 feet where temperatures are typically minus 65 degrees Fahrenheit, the speed of sound drops to about 660 miles per hour. When an aircraft flies slower than the speed of sound, in what aeronautical engineers call the subsonic regime, it pushes air out of its way, and that air has time to flow smoothly around the aircraft. The pressure disturbances created by the aircraft propagate ahead of it at the speed of sound, giving the oncoming air advance warning, so to speak, that the aircraft is approaching. The air smoothly divides and flows around the aircraft, then comes back together behind it. But when an aircraft accelerates to the speed of sound, something fundamental changes. The pressure disturbances it creates can no longer move ahead of the aircraft because the aircraft itself is moving at the same speed the disturbances propagate. And when the aircraft exceeds the speed of sound, when it goes supersonic, those pressure disturbances pile up at the aircraft's leading edges, creating shock waves. A shock wave is a mathematical discontinuity in the properties of air. Across a shock wave, which is only a few molecules thick, pressure, temperature, and density change nearly instantaneously. These aren't gradual transitions, they're sharp, abrupt changes. Before the shock wave, the air is at one state. After the shock wave, the air is at a completely different state. And because these changes are so abrupt, they carry a tremendous amount of acoustic energy. For a supersonic aircraft, the primary shock waves form at the nose, where air first encounters the aircraft, and at the tail, where the airflow returns to its original state. But shock waves also form at other points on the aircraft, where the geometry changes significantly, particularly at the wings, engine inlets, and canopy. All of these shock waves propagate outward from the aircraft in a cone shape. The angle of this cone, called the Mach cone or Mach angle, depends on the aircraft's speed. The faster the aircraft flies, the narrower the cone becomes. As these shock waves propagate away from the aircraft, something interesting happens. The multiple shock waves generated by different parts of the aircraft tend to merge and coalesce. By the time the shock waves have travelled a few hundred feet from the aircraft, they've typically combined into just two main shocks: the bow shock from the front of the aircraft and the tail shock from the rear. This creates the characteristic N-wave pressure signature. The N-wave gets its name from its shape when plotted on a graph. Starting at ambient atmospheric pressure, there's a sharp rise in pressure as the bow shock passes. Then the pressure gradually decreases, dropping below ambient as the expansion waves from the middle of the aircraft arrive. Finally, there's another sharp rise back to ambient pressure as the tail shock passes. When you draw this pattern, it looks roughly like the letter N, hence the name. When this N wave reaches the ground, those two sharp pressure rises, the bow shock and tail shock, create the characteristic double boom that people hear. The first boom is from the nose shock, the second from the tail shock. Depending on the aircraft's altitude and speed, these two booms might be separated by anywhere from 1/10 of a second to half a second. To human ears, they often sound like a single extended boom rather than two distinct sounds. The strength of the sonic boom depends on several factors. Larger aircraft generate stronger booms because they displace more air. Faster aircraft generate stronger booms because the shock waves are more intense. Aircraft flying at lower altitudes generate stronger booms because the shock waves have less distance to dissipate. And critically, the shape of the aircraft matters tremendously. This last point, the influence of aircraft shape on sonic boom strength, is where our story becomes particularly interesting. Because while the first three factors, size, speed, and altitude, are relatively straightforward, the effect of shape is much more subtle and complex. For decades, sonic boom researchers had understood that aircraft shape influenced boom strength, but they didn't fully understand the mechanisms involved or how to exploit them to reduce the boom. The key insight came from understanding how shock waves form and coalesce as they propagate away from the aircraft. In the immediate vicinity of the aircraft, called the near field, there are multiple shock waves from different parts of the aircraft, but as these waves travel outward, they begin to merge. The way they merge depends critically on the distribution of volume and lift along the length of the aircraft. If the aircraft has a sharp nose and a lot of volume concentrated near the front, the bow shock will be very strong. If volume and lift are distributed more evenly along the aircraft's length, the shock waves spread out and don't coalesce as strongly. This phenomenon is governed by what's called the sonic boom equivalent area distribution. This is a mathematical function that describes how an aircraft's volume and lift distribution translate into shock wave strength. By carefully controlling this area distribution, by shaping the aircraft so that volume and lift increase gradually from nose to tail rather than in abrupt steps, it's possible to prevent shock waves from merging into a strong bow shock. In 1967, two researchers at Cornell University, Arkansas, George and Richard Seabass, published a landmark paper that laid the theoretical foundation for sonic boom minimization through aircraft shaping. They proved mathematically that for any given aircraft length and weight, there exists an optimal shape that minimizes the maximum overpressure of the sonic boom. This optimal shape produces what they called a flat top signature rather than the traditional N wave. The flat top signature still has a bow shock and a tail shock, but between them, instead of a smooth decrease in pressure, there's a plateau. The pressure rises relatively slowly at the front, stays roughly constant for a period, and then decreases back to ambient. This spreading out of the pressure rise over a longer time period significantly reduces the perceived loudness of the boom. More pressure change over more time equals less acoustic power and a quieter boom. The George Seabass theory predicted that a properly shaped aircraft could reduce the perceived loudness of its sonic boom by significant margins, potentially by half or more compared to a conventional aircraft of the same size and speed. But there was a catch. The aircraft shapes required to achieve these flat-top signatures were unconventional, to say the least. They typically required very long, slender noses that gradually increased in volume, carefully controlled distribution of lift along the aircraft's length, and precisely shaped underbody fairings that modified the volume distribution in just the right way. For more than 30 years after the George Seabass paper was published, their theory remained largely academic. The shapes required were so unconventional that nobody was willing to bet the enormous resources required to design, build, and test an actual aircraft. Computational fluid dynamics wasn't advanced enough to validate the theory with confidence. Wind tunnel tests could only provide limited information, and most critically, there was no market for supersonic aircraft that would justify the investment. But the theory didn't die. Through the 1970s, 80s and 90s, a small community of researchers continued working on sonic boom minimization. They refined the theory, developed more sophisticated propagation models that accounted for atmospheric effects, and created design methods that could translate the abstract mathematics of area distributions into actual aircraft shapes. They conducted limited experiments using nose booms mounted on aircraft to probe shock waves in flight. They used increasingly powerful computers to run computational fluid dynamics analyses that simulated supersonic flow fields with growing accuracy. By the late 1990s, computational fluid dynamics had advanced to the point where researchers could design aircraft shapes with reasonable confidence that they would produce the predicted sonic boom signatures. Computer codes could model the complex three-dimensional flow around supersonic aircraft, tracking how shock waves formed, propagated, and coalesced. They could predict pressure signatures at various distances from the aircraft. They could even simulate how those signatures would change as they propagated through realistic atmospheric conditions to the ground. These advances in computational capability came at an opportune time. In the late 1990s, there was renewed interest in supersonic commercial aviation. The Concorde had proven that supersonic transport was technically feasible and that there was a market, albeit limited, for ultra-fast long-distance travel. Several aerospace companies began studying supersonic business jets that could serve the corporate market. These aircraft, smaller and more economical than a supersonic transport, might be commercially viable even with restrictions on overland supersonic flight. But if the sonic boom could be reduced enough to allow overland flight, the market would expand dramatically. This renewed interest in supersonic aviation caught the attention of the Defense Advanced Research Projects Agency, the Pentagon's advanced research arm. DARPA had been founded in 1958 in response to the Soviet Union's launch of Sputnik. Its mission was to prevent technological surprise and maintain American military superiority through breakthrough technologies. While DARPA was primarily focused on military applications, it also funded research with potential civilian benefits, especially in areas like aviation, where military and civilian technologies overlapped significantly. In the late 1990s, DARPA began looking at the sonic boom problem from a fresh perspective. They recognized that if sonic booms could be reduced to acceptable levels, it would enable not just commercial supersonic aviation, but also military applications. A supersonic reconnaissance or strike aircraft that could fly over populated areas without creating a disturbing boom would have tremendous operational flexibility. It could conduct missions anywhere in the world without the political complications that came from generating sonic booms over friendly territory. More immediately, DARPA saw an opportunity to validate decades of theoretical research with actual flight tests. The computational tools now existed to design an aircraft with a shaped boom. The manufacturing techniques existed to build such an aircraft, and the cost of demonstrating the concept, while substantial, was achievable if an existing aircraft could be modified rather than building something entirely new. All that was needed was the will to do it and the funding to make it happen. That will and that funding would come together in a program called the Quiet Supersonic Platform, which would eventually lead to the historic flights over Edwards Air Force Base in August of 2003. But before we can tell that story, we need to understand more about the remarkable aircraft that would become the shaped sonic boom demonstrator, the Northrop F-5 Tiger II. The Iron Tiger, the Northrop F-5E's journey to sonic boom research. The aircraft that would eventually prove sonic boom shaping was possible had a long and distinguished history that had nothing to do with sonic booms. The Northrop F-5 Tiger II was designed in the late 1960s as an affordable, lightweight fighter for US allies. It became one of the most successful military aircraft exports in history, serving with air forces around the world for more than 5 decades. That one of these rugged fighters would end up as a testbed for revolutionary sonic boom research is a story of opportunity, practicality, and the Air Force's habit of finding new uses for old aircraft. The story of the F-5 begins in the mid-1950s, when Northrop Corporation began studying lightweight supersonic fighter designs. At the time, American fighters were growing larger, heavier, and more expensive. Aircraft like the F-4 Phantom II and F-105 Thunderchief were magnificent machines, but they were also complex and costly. Northrop believed there was a market for a simpler, cheaper fighter that could still perform well in combat. They envisioned an aircraft that would be easy to maintain, operate from rough airfields, and cost a fraction of what the high-end fighters cost. In 1955, a Northrop team toured Europe and Asia to study the defense needs of NATO and SEATO countries. They found that many Allied nations wanted supersonic fighters, but couldn't afford the sophisticated aircraft in the American inventory. Northrop's design study produced a concept for a lightweight supersonic fighter that would be relatively inexpensive, require minimal infrastructure, and be simple enough that pilots and ground crews with limited training could operate it effectively. The Air Force wasn't particularly interested in the fighter version initially, but they did need a new advanced trainer to replace the aging T-33. Northrop's design was adapted to create the T-38 Talon, which first flew in 1959 and became the standard Air Force jet trainer. The T-38 was sleek, fast, and economical to operate. It proved the basic soundness of Northrop's lightweight supersonic design philosophy. In April of 1962, the Department of Defense selected Northrop's fighter design for the Military Assistance Program. The aircraft, designated F-5A Freedom Fighter, would be provided to American allies as part of foreign military aid. It was optimized for air-to-ground missions and had only limited air-to-air capability. The first production F-5As were delivered in 1964. In 1965, in a program codenamed Scotia Tiger, the Air Force borrowed 12 F-5As and sent them to Vietnam for combat evaluation. The aircraft performed well, proving reliable and effective in the close air support role. It was during this deployment that the F-5 gained its Tiger nickname. After the evaluation, the aircraft were turned over to the South Vietnamese Air Force. By the late 1960s, the F-5A was showing its age. More capable Soviet fighters, particularly improved versions of the MiG-21, were being deployed to Soviet allies and client states. American allies needed a more capable fighter to maintain air superiority. In 1968, the Department of Defense launched the International Fighter Aircraft Program to find a replacement for the F-5A. The emphasis was on air-to-air combat capability against the latest Soviet fighters. Northrop entered an improved version of the F-5A, initially called the F-5A-21. The design featured more powerful General Electric J8521 engines producing 5,000 pounds of thrust each with afterburner, compared to 4,080 pounds for the engines in the F-5A. The fuselage was lengthened and enlarged to accommodate more fuel, extending range and endurance. Most significantly, the wings were extensively redesigned with enlarged leading-edge extensions that gave increased wing area and dramatically improved maneuverability. The new design also incorporated a radar, the Emerson Electric AIN APQ 153, giving the aircraft a beyond visual range engagement capability the F-5A lacked. The avionics were more sophisticated overall, with improved weapons delivery systems, navigation equipment, and defensive systems. Two M39 20mm cannons were mounted in the nose, and the aircraft could carry air-to-air missiles, rockets, bombs, and other ordnance on 7 external hardpoints. In November of 1970, Northrop won the International Fighter Aircraft Competition. The aircraft was officially designated F-5E, and it came to be known as the Tiger II. The first F-5E flew in August of 1972. Production continued until 1987, with a total of about 1,400 Tiger IIs built. The aircraft was exported to more than 30 countries, serving with distinction in air forces around the world. The F-5E was 48 feet 2 inches long, with a wingspan of 26 feet 8 inches. Empty weight was about 9,700 pounds, with a maximum takeoff weight of 24,675 pounds. With its powerful engines and relatively light weight, the F-5E had excellent performance. Maximum speed was Mach 1.63 at altitude, about 1,080 miles per hour. Service ceiling was over 50,000 feet. Range with external fuel tanks exceeded 1,400 nautical miles. But what made the F-5E particularly attractive for its role as a fighter wasn't just its performance specifications, it was the aircraft's handling qualities. The F-5E was known for being exceptionally pleasant to fly, with light, responsive controls and predictable behavior throughout its flight envelope. It was docile enough that relatively inexperienced pilots could fly it safely, yet capable enough that skilled pilots could use it to perform advanced maneuvers. The aircraft's small size and excellent maneuverability made it similar in some respects to the Soviet MiG-21, which led to an interesting secondary use. The US Air Force and Navy began using F-5Es as aggressor aircraft for dissimilar air combat training. Painted in Soviet-style camouflage schemes and flown using Soviet tactics, F-5Es played the role of enemy fighters in training exercises. American fighter pilots would practice engaging these aggressor aircraft to prepare for potential combat against Soviet-equipped forces. This program proved so valuable that aggressor squadrons flying F-5Es became a permanent fixture at bases like Nellis Air Force Base in Nevada and NAS Fallon in Nevada. One of these aggressor F-5Es, Bureau number 741519, was built in 1974 and initially delivered to the South Vietnamese Air Force. When South Vietnam fell in 1975, the aircraft was turned over to the US Air Force. It served for several years as an aggressor aircraft before being transferred to the Navy in 1989 or 90. The Navy used it for adversary training at various facilities, continuing the mission of helping prepare American fighter pilots for combat. By the late 1990s, 741519 had accumulated thousands of flight hours, but was still in good mechanical condition. It was one of dozens of F-5Es in Navy service, used for training but not considered particularly special. When DARPA began looking for an aircraft to serve as a testbed for sonic boom shaping research, the F-5E came up as a strong candidate for several practical reasons. First, the F-5E was supersonic and relatively small, making it suitable for the speeds and altitudes at which a supersonic business jet might operate. It could reach Mach 1.4 or slightly higher, which was appropriate for the research program. It was small enough that modifying it would be less expensive than working with a larger aircraft. And crucially, the F-5E had a modular design that made it relatively straightforward to replace sections of the fuselage. Second, F-5Es were available. The Navy had dozens of them, and they were willing to loan one for research purposes. The aircraft were well understood from an engineering standpoint, with extensive documentation available. Spare parts were readily available. Maintenance procedures were well established. All of this would make the modification and flight test program much easier than working with a more exotic or rare aircraft type. Third, and perhaps most importantly, the F-5E had a relatively simple baseline configuration from a supersonic aerodynamic standpoint. It wasn't designed with area ruling or other sophisticated supersonic optimization techniques. Its sonic boom signature was a straightforward N wave, typical of conventional supersonic aircraft. This made it an ideal baseline for comparison. Any changes to the boom signature could be clearly attributed to the modifications made for the demonstration program. When DARPA issued its Quiet Supersonic Platform Program solicitation in 2000, several aircraft types were considered as potential test beds. These included unmanned aerial vehicles like the Teledyne Ryan BQM-34E Firebee, which was supersonic and remotely piloted. Some teams proposed using modified business jets or even building entirely new demonstration aircraft. But Northrop Grumman's proposal to modify an F-5E offered the best combination of technical suitability, risk management, cost control, and schedule certainty. The F-5E could be modified extensively without requiring a complete redesign. Its nose section could be replaced with a longer, carefully shaped section designed to create a flat-top sonic boom signature. Fairings could be added to the underbody to modify the aircraft's volume distribution. These modifications would change the aircraft's supersonic characteristics significantly, but they wouldn't require changes to the wings, engines, or primary flight control systems. The modified aircraft would still handle like an F-5E, just with different external contours. In July of 2001, DARPA awarded Northrop Grumman a contract to design, modify, and fly an F-5E as part of the Shaped Sonic Boom demonstration program. The US Navy agreed to loan Bureau No. 7 41519 for the project through a cooperative research and development agreement. The aircraft was flown to Northrop Grumman's St. Augustine, Florida facility, where the company performed F-5 depot maintenance work for the Navy. There, teams of engineers and technicians would spend the next 2 years transforming this veteran fighter into the world's first aircraft designed to generate a shaped sonic boom. The selection of this particular F-5E, now given the designation F-5 SSBD for Shaped Sonic Boom Demonstrator, set the stage for everything that followed. This aircraft, with thousands of hours of military service behind it, would become the platform for validating decades of theoretical research. It would prove that sonic booms could be shaped and reduced, and in doing so, it would potentially change the future of aviation. Designing Thunder, creating the Shaped Sonic Boom Demonstrator. The transformation of a standard F-5E fighter into the world's first shaped sonic boom demonstrator was an engineering challenge of remarkable complexity. The goal was deceptively simple: modify the aircraft's shape so that it would generate a flat-top sonic boom signature instead of a conventional N wave. But achieving that goal required integrating theoretical aerodynamics, advanced computational fluid dynamics, structural engineering, and practical aircraft modification techniques into a coherent design that could actually fly safely and produce the desired results. The work began at Northrop Grumman's El Segundo, California facility in late 2001, immediately after DARPA awarded the contract. The company assembled a team of some of its best aerodynamicists, structures engineers, manufacturing specialists, and flight test engineers. The program manager was Charles Boccadoro, a veteran aerospace engineer with extensive experience managing complex development programs. The chief engineer was David Graham, an expert in supersonic aerodynamics and sonic boom physics. The chief test pilot would be Roy Martin, who had more than 9,000 hours of flight time and decades of experience flying the F-5. The team's first challenge was translating the abstract mathematics of sonic boom minimization into an actual aircraft shape. The George Seabass theory provided the theoretical foundation, predicting that an optimal shape could reduce sonic boom overpressure significantly. But the theory didn't directly specify what that shape should look like. It provided design principles and optimization criteria, but the actual design process required extensive computational work. The key was to control what's called the equivalent area distribution. This is a mathematical representation of how an aircraft's volume and lift, as seen from the direction of flight, vary along its length. For a conventional aircraft with a blunt nose, significant volume near the cockpit, and wings positioned well aft, the equivalent area increases in steps. These steps cause shock waves to coalesce into a strong bow shock, resulting in a traditional N-wave sonic boom. To create a flat top signature, the equivalent area needed to increase much more gradually from nose to tail. This required lengthening the nose significantly, distributing volume more evenly along the fuselage, and carefully shaping the underside of the aircraft to modify how the volume distribution appeared from below. The challenge was doing all of this while maintaining the aircraft's basic flight characteristics and without requiring modifications so extensive that the project would become prohibitively expensive or schedule would slip unacceptably. The design team used Northrop Grumman's advanced computational fluid dynamics codes to explore various configurations. These codes could simulate the three-dimensional supersonic flow field around the aircraft, tracking how shock waves formed and propagated. The simulations ran on powerful computer clusters and could take hours or even days to complete for each configuration. The team would run a simulation, analyze the results, adjust the design, and run another simulation. Through hundreds of iterations, they gradually converged on a configuration that produced the desired flat-top signature. The final design featured several key modifications. The most obvious was a dramatically extended nose section. Where the standard F-5E had a relatively blunt conical nose about 6 feet long, the modified aircraft would have a streamlined nose over 14 feet long. This nose wasn't just longer, it was carefully sculpted so that its cross-sectional area increased gradually and smoothly from the tip back to where it mated with the original fuselage. The shape resembled a pelican's bill, which led some team members to nickname the modified aircraft the Pelican. The extended nose solved part of the problem, but not all of it. The wings and engine inlets of the F-5E would still generate shock waves that could coalesce with the bow shock if nothing was done to prevent it. To address this, the design team developed an elaborate underbody fairing system. These fairings, which would be attached to the underside of the forward fuselage, carefully added volume in specific locations to modify the equivalent area distribution. The underbody fairings were among the most intricate parts of the modification. They had to be shaped precisely to produce the right volume distribution, but they also had to integrate smoothly with the existing structure without creating any discontinuities or sharp edges that might generate unwanted shock waves. They had to be strong enough to withstand the aerodynamic loads during supersonic flight, but light enough not to significantly change the aircraft's weight and balance. And they had to be manufactured with high precision, because even small deviations from the design shape could alter the sonic boom signature. To validate their design, the team used multiple computational approaches. The primary tool was a sophisticated code called GASP, which could solve the Navier-Stokes equations governing fluid flow around the aircraft. These simulations predicted the shockwave patterns in the near field close to the aircraft. Then the team used specialized sonic boom propagation codes to predict how those shockwaves would evolve as they traveled through the atmosphere to the ground. One particular challenge was accounting for the F-5E's engines. The General Electric J85 engines were mounted in the aft fuselage, with their inlets on the sides of the aircraft just aft of the cockpit. These inlets would generate strong shockwaves during supersonic flight. The underbody fairings had to be designed to partially compensate for the volume and pressure changes created by the engine inlets, smoothing out the equivalent area distribution so that the inlet shocks didn't create a spike in the sonic boom signature. Another complexity was dealing with off-design conditions. The F-5 SSBD was being designed to produce a flat-top signature at a specific cruise condition, Mach 1.4 at 32,000 feet. At this condition, the aircraft would generate a particular lift coefficient and angle of attack. The modifications were optimized for these specific conditions, but the aircraft would have to fly through a wide range of speeds and altitudes during takeoff, climb, acceleration, and landing. The design team had to ensure that the modifications wouldn't create any dangerous aerodynamic characteristics at these off-design conditions. Wind tunnel tests provided crucial validation of the computational predictions. Northrop Grumman conducted tests using scale models of the modified F-5E in supersonic wind tunnels. These tests measured pressure distributions on the aircraft surface, shockwave angles, and aerodynamic forces. The wind tunnel data generally confirmed the computational predictions, giving the team confidence that their design would work as intended. But the wind tunnel tests also revealed some discrepancies that required design adjustments. One concern that emerged during the design phase was the effect of the modifications on the aircraft's handling qualities. The extended nose would move the center of gravity forward, potentially affecting the aircraft's stability and control. The underbody fairings would change the aircraft's directional stability, particularly at high angles of attack. The increased cross-sectional area in some regions would increase drag, potentially limiting the aircraft's maximum speed or endurance. To address these concerns, the design team conducted extensive analyses of the modified aircraft's stability and control characteristics. They used 6 degree of freedom flight simulation tools to predict how the aircraft would handle throughout its flight envelope. They identified that directional stability would be somewhat reduced, but still within acceptable limits. They determined that the increased drag would limit the aircraft's maximum Mach number to about 1.4 at 32,000 feet, compared to 1.63 for a standard F-5E, but this was acceptable since the demonstration flights were planned for Mach 1.4 anyway. Once the design was finalized and validated through computational analyses and wind tunnel tests, the actual modification work could begin. In late 2002, the F-5E was flown to Northrop Grumman's facility in St. Augustine, Florida, where the company had extensive experience performing depot-level maintenance on F-5 aircraft. There, skilled technicians would carry out the physical transformation of the aircraft. The modification process was extensive and complex. The first step was to remove the original nose section. This required cutting the fuselage just forward of the cockpit and carefully detaching all the systems that ran through that area, including hydraulic lines, electrical wiring, and environmental control ducting. The cut had to be precise because the new nose section would mate to the structure at this point. The new extended nose section was fabricated at Northrop Grumman's El Segundo facility using advanced composite materials. The structure consisted of aluminum frames and bulkheads covered with composite skin panels. Composite materials were chosen because they could be formed into the complex curved shapes required while being lighter than equivalent metal structures. The nose was hollow, with internal structure to provide strength and stiffness, but it didn't house any significant systems. Its purpose was purely aerodynamic, to shape the airflow and shock waves in the desired way. Installing the new nose required precise alignment to ensure it would be perfectly symmetrical and properly positioned relative to the rest of the aircraft. Any asymmetry or misalignment could create unwanted aerodynamic forces or affect the aircraft's handling. Special jigs and fixtures were built to hold the nose in exact position while it was permanently attached to the fuselage structure. The joint between the new nose and original fuselage was carefully faired and smoothed to eliminate any steps or gaps. The underbody fairings were even more challenging to install. There were multiple fairings of different shapes and sizes, each designed to add volume in specific locations to achieve the desired equivalent area distribution. These fairings were fabricated from composite materials and attached to the underside of the forward fuselage using hundreds of fasteners. Like the nose, they had to be installed with great precision to match the design shape exactly. The installation process was painstaking. Each fairing had to be positioned carefully, drilled for mounting holes without damaging the underlying structure, and fastened securely. The joints between fairings had to be sealed and smoothed. The entire assembly had to be checked repeatedly with precision measuring equipment to verify that it matched the design specifications within tight tolerances. Even small deviations could affect the sonic boom signature. Beyond the aerodynamic modifications, the F-5 SSBD required extensive instrumentation to collect data during flight tests. A sophisticated GPS-based tracking system was installed to record the aircraft's exact position, altitude, and velocity during supersonic runs. This system used dual GPS receivers and advanced post-processing techniques to achieve centimeter-level accuracy in position measurements. Pressure sensors were installed at various points on the aircraft's surface to measure the pressure distributions during supersonic flight. Temperature sensors would monitor structural heating. Accelerometers would track the aircraft's motion and any vibrations. The aircraft also needed an upgraded telemetry system to transmit flight data in real time to ground stations. During the actual sonic boom measurement flights, engineers on the ground would need to see the aircraft's position, speed, and flight path in real time so they could confirm that the flight profile was being executed correctly. The telemetry system had to be reliable and capable of transmitting large amounts of data continuously during flight. As the modification work progressed through 2003, the project encountered its share of challenges. Some parts didn't fit quite right on the first attempt and had to be reworked. The schedule slipped as unexpected complications arose. The budget grew as the scope of work expanded to address issues that hadn't been fully appreciated during the design phase. But slowly, steadily, the transformation progressed. By early summer of 2003, the physical modifications were complete. The aircraft looked dramatically different from a standard F-5E. The long, streamlined nose gave it an unmistakable profile. The underbody fairings created a unique silhouette when viewed from below. To celebrate the achievement and make the aircraft's purpose obvious, the design team came up with a distinctive paint scheme. The aircraft was painted white with blue stripes running along the fuselage. But these weren't just decorative stripes. One stripe represented the traditional N-wave sonic boom signature of a standard F-5E. The other represented the flat-top signature the modified aircraft was designed to create. Anyone who saw the aircraft would immediately understand its mission. Now came the crucial question: would it actually work? After 2 years of design, analysis, fabrication, and assembly, after millions of dollars spent and thousands of hours of work by hundreds of people, would this modified F-5E actually generate a shaped sonic boom? Would the theories, computational predictions, and wind tunnel results translate into reality? There was only one way to find out: fly it and measure the results. But before that could happen, a great deal more preparation was necessary. The aircraft had to be thoroughly inspected and certified as safe to fly. A comprehensive test plan had to be developed. Instrumentation had to be installed at ground sites to measure the sonic booms. Chase aircraft had to be prepared and instrumented to measure the shock waves in flight. Weather conditions had to be monitored to identify optimal times for testing. And the entire team had to coordinate their efforts across multiple locations and organizations. The historic flights of August 2003 were still weeks away. The journey to Palmdale, preparing for the moment of truth. With the physical modifications to the F-5 SSBD complete by midsummer of 2003, the project entered a new phase. Preparing for the actual flight tests that would determine whether the theories, analyses, and engineering work of the past 2 years would translate into success. This preparation phase involved an intricate choreography of aircraft testing, sensor deployment, personnel coordination, and weather monitoring. It also involved a literal journey, as the modified F-5E would have to fly from Florida to California, where the flight tests would be conducted. The choice of Edwards Air Force Base in California as the flight test location was almost inevitable. Edwards had been the heart of American high-speed flight research since the 1940s. It was where Chuck Yeager broke the sound barrier in 1947. It was where the X-15 rocket plane reached the edge of space. It was where every major American experimental aircraft from the past 60 years had been tested. The base offered something that few other locations could: restricted airspace where supersonic flight was permitted, year-round good weather, vast expanses of unpopulated desert, and world-class technical facilities. More specifically, Edwards had supersonic corridors, defined blocks of airspace where aircraft could fly supersonic for test purposes. These corridors ran for dozens of miles over sparsely populated areas, allowing aircraft to maintain supersonic speeds long enough to generate steady sonic boom carpets on the ground. The base was also home to NASA's Dryden Flight Research Center, which had extensive experience with sonic boom research and could provide crucial support for the SSBD program. But before the F-5 SSBD could fly to California, it had to prove that it could fly safely. The modifications had changed the aircraft's aerodynamics significantly. While computational analyses and wind tunnel tests suggested the aircraft would handle acceptably, there was no substitute for actual flight testing. This meant conducting functional check flights in Florida first to verify the aircraft's basic airworthiness and handling qualities before attempting the cross-country ferry flight. On July 24, 2003, the moment arrived. The weather was favorable in the Jacksonville area, with temperatures in the 70s climbing toward highs in the upper 80s. Humidity was high, but visibility was good. Roy Martin, Northrop Grumman's chief test pilot, climbed into the F-5 SSBD's cockpit at the company's St. Augustine facility for the first time. Behind him, many of his colleagues watched with a mixture of excitement and anxiety. 2 years of work were about to face the ultimate test. Martin began his taxi from Northrop Grumman's facility to the St. Johns County Airport's 8,000-foot runway. The aircraft felt different from a standard F-5E, with the weight distribution changed by the extended nose and underbody fairings. But the taxi was normal. Martin performed his pre-takeoff checks, confirmed that all systems were functioning properly, and advanced the throttles. The twin General Electric J-85 engines spooled up to full military power, and the F-5 SSBD began its takeoff roll. The aircraft accelerated smoothly and lifted off without incident. Mike Bryan, flying a Northrop Grumman T-38 chase plane with John Nevedomsky in the back seat, joined up with the F-5 SSBD as it climbed away from the airport. Together they flew into restricted airspace off the Atlantic coast for the functional check flight. Martin went through a series of maneuvers designed to evaluate the aircraft's handling qualities at various speeds and altitudes. He checked the stability augmentation system, performed pitch and yaw maneuvers, and generally got a feel for how the modified aircraft flew. As predicted by the pre-flight analyses, the F-5 SSBD displayed slightly reduced directional stability compared to a standard F-5E, but nothing unexpected or problematic. The handling qualities were well within acceptable limits. Most importantly, Martin was able to push the aircraft through the sound barrier, reaching Mach 1.1 even in the hot summer temperatures that were degrading engine performance. This confirmed that the modifications, despite increasing drag, hadn't prevented the aircraft from achieving supersonic flight. After about an hour of flying, both aircraft landed at Cecil Field, a former naval air station on Jacksonville's western edge, with a 12,500-foot runway. This would serve as their temporary base for the next several days, as additional functional check flights were conducted. 2 more flights followed on July 27th and the morning of July 28th, further expanding the envelope of conditions in which the aircraft had been tested. These local test flights served multiple purposes beyond just checking handling qualities. They verified that the aircraft's new air data systems were reading correctly. They confirmed that telemetry from the onboard instruments was reaching the temporary ground station set up at St. Augustine. They provided Roy Martin with valuable experience flying this unique aircraft, building his confidence in its behavior and characteristics. And critically, they demonstrated that all systems were working properly for the upcoming cross-country ferry flight to California. On the afternoon of July 28th, having successfully completed the final local sortie earlier that morning, the F-5 SSBD and its T-38 escort began their journey west. They would make 4 stops along the way, breaking the 2,200-mile trip into manageable legs. The route took them across the southeastern United States, then west through Texas and New Mexico. Each leg required careful fuel planning, weather monitoring, and coordination with air traffic control. The journey wasn't without its adventures. Summer weather in the southern United States can be unpredictable, with afternoon thunderstorms building rapidly. The pilots had to navigate around weather at several points during the trip. At one point, they had to divert to avoid a particularly strong storm cell. But the 2 aircraft pressed on, and on Tuesday afternoon, July 29th, they approached their destination. As they descended toward Palmdale, the pilots could see a rare summer thunderstorm building over Lancaster, creating dramatic cloud formations in the clear desert air. They navigated carefully around the weather and touched down gracefully on the runway at Air Force Plant 42. They had made it. After 2 years of design and fabrication work in Florida and El Segundo, after a week of test flights in Florida, after a 2-day ferry flight across the country, the shaped sonic boom demonstrator had arrived at the location where it would make history. Air Force Plant 42 is a sprawling 5,800-acre facility hosting multiple aerospace companies. Northrop Grumman occupied facilities in Sites 3 and 4. Site 4 included Building 401, the massive structure where the company had assembled its B-2 stealth bombers in complete secrecy during the 1980s. The SSBD team would operate out of a section of Building 307 in Site 3. After landing, the F-5 SSBD and its T-38 escort taxied to Site 3, where they were met by maintenance crews and Northrop Grumman engineers from El Segundo who were eager to see the finished aircraft. The aircraft was quickly moved into the shelter of Building 307 as the threatening storm approached. That evening, Roy Martin drove to his home in nearby Lancaster and discovered that the unseasonal storm had been severe enough to uproot large trees onto 2 of his neighbors' homes. The storm was a reminder that even in the usually benign desert climate, weather could pose challenges for flight operations. Weather would prove to be more than just a nuisance. It would become a significant concern for the entire demonstration program. Weather balloons launched from Edwards and other nearby facilities were measuring atmospheric temperatures at altitude, and the readings were alarming. The temperatures at the planned flight test altitude of 32,000 feet were running about 17 degrees Celsius, that's 30.6 degrees Fahrenheit, higher than the standard atmosphere temperature that the modification design had assumed. The standard temperature at 32,000 feet is about -48.5 degrees Fahrenheit, but measurements were showing temperatures around -18 degrees. This temperature difference was more than just a curiosity. It had serious implications for the demonstration. The F-5 SSBD had been designed to fly at Mach 1.4 at 32,000 feet. At this design condition, the aircraft would generate its optimal flat-top sonic boom signature. But aircraft engine performance degrades in hot temperatures because the air is less dense. The hotter air would make it difficult for the F-5 SSBD to reach Mach 1.4, potentially limiting the demonstration to lower Mach numbers where the sonic boom shaping might not be as effective. The unusually warm temperatures were part of an abnormal weather pattern affecting the western United States that summer. Some members of the SSBD working group began recommending that the flight tests be postponed until November, when upper atmosphere temperatures would be more favourable. From a purely technical standpoint, this made sense. Why conduct the demonstration under conditions that would limit the aircraft's performance? But Charles Boccadoro, the Northrop Grumman program manager, had to consider factors beyond pure technical optimization. The project was already behind schedule and over budget. Senior corporate management was watching the program closely. The Navy had loaned the F-5E for a specific period, and extending that loan would require additional negotiations. The team of engineers and technicians assembled for the flight tests couldn't be kept on standby indefinitely, and perhaps most critically, there was momentum that would be lost if the demonstration was delayed. Boccadoro made the decision to proceed, telling his team that time was their enemy. As he later explained, being behind schedule and over budget is true hell for a program manager. Delaying further would only make the situation worse. If the hot weather meant they couldn't reach Mach 1.4, they would demonstrate the shaped boom at whatever speed the aircraft could achieve. It might not be perfect, but it would still prove the concept. To give the aircraft the best possible chance of reaching the desired speed, Boccadoro reached out to the Naval Air Systems Command Propulsion Directorate and General Electric Aviation's Engine Maintenance Division. He secured permission for Northrop Grumman technicians, led by the company's flight test engineer William Thorne, to perform what's called a compressor wash and uptrim on the F-5 SSBD's engines. This maintenance procedure would clean deposits out of the compressor blades and adjust the engine controls to extract maximum thrust. It was essentially tuning the engines for peak performance. While engine work proceeded, the team conducted additional functional check flights starting on Saturday, August 2nd. Roy Martin and Commander Darrell Spike Long, the Navy's chief test pilot from Naval Air Weapons Station China Lake, would alternate as pilots for the F-5 SSBD during the demonstration program. With Mike Bryan having returned Boeing's T-38 to Seattle, a NASA Dryden FA-18 piloted by Jim Smolka would fly chase. These flights focused on supersonic envelope expansion, pushing the aircraft to higher Mach numbers at altitude to further characterize its performance. The flights confirmed that the handling qualities were acceptable throughout the flight envelope. They provided additional experience for both pilots in flying this unique aircraft. They validated the telemetry systems and data collection procedures, and they gave the ground crews experience in turning the aircraft around quickly between flights. These shakedown flights were invaluable for identifying and fixing minor issues before the critical sonic boom measurement flights began. Meanwhile, a major effort was underway to prepare the ground instrumentation that would measure the sonic booms. Ed Herring from NASA Dryden was leading this effort, coordinating with specialists from NASA Langley, Weil Laboratories, and other organizations. They had identified an area under the Edwards high-altitude supersonic corridor where they would deploy an extensive array of sensors. The site they chose was along Cords Road, running east to west under the restricted airspace about 30 miles north of California Highway 58 between Barstow and Boron. Preparing this remote desert site proved unexpectedly complicated. The land was divided into a checkerboard pattern of Bureau of Land Management property and private holdings. Because privately owned sections were difficult to coordinate, the planners limited their sensor sites to BLM land. But even using public land required extensive coordination and permits because the area was habitat for threatened and endangered species, most notably the desert tortoise and Mojave ground squirrel. Starting in fall of 2002, Ed Herring and Mike Beck, the environmental specialist at NASA Dryden, spent months working with the BLM office in Barstow and Edwards Air Force Base Environmental Management to obtain the necessary permits and meet environmental requirements. All personnel who would work on the sensor array had to receive desert tortoise protection training. A BLM-approved biologist had to oversee site selections and be present during equipment setup and removal. Vehicles were prohibited from driving off existing roads, and when desert tortoises were encountered on roads, which happened several times, they could not be moved. Personnel had to wait patiently for the tortoises to move on their own. The sensor array was designed to provide comprehensive measurements of the sonic booms from both the modified F-5 SSBD and a standard F-5E baseline aircraft. The sensors were arranged in and around 3 major sites designated west, center, and east along a 6-mile stretch of Cords Road, with additional sites to the north and south. The equipment included ultra-sensitive BRA 144L and KR microphones capable of measuring very low-frequency pressure changes, specially designed boom amplitude and direction sensor systems that could determine the angle at which shock waves arrived, and numerous recording and data acquisition systems. NASA Langley provided an acoustic instrumentation van with sophisticated recording equipment, while laboratories brought similar capabilities. NASA Dryden contributed multiple sensor systems and recording devices. All of this equipment, along with generators, battery packs, cables, portable toilets, and other support items, had to be transported to the remote desert locations and set up according to precise specifications. The sensor positions were surveyed using GPS to determine their exact coordinates. Each sensor system was carefully calibrated. Because the equipment would be left unattended in this isolated area, security was a concern. Northrop Grumman hired armed guards to watch over the sites when personnel weren't present. As the security contractor explained, equipment left alone for a few days would probably be stripped clean. The guards became a constant presence at the sites, protecting the valuable instruments from theft or vandalism. By late August, after weeks of preparation, everything was finally in place. The F-5 SSBD had been thoroughly tested and was ready for the sonic boom measurement flights. The engines had been tuned to maximum performance. The ground sensor array had been deployed and tested. Personnel from Northrop Grumman, NASA Dryden, NASA Langley, Weil Labs, and other organizations were in position. Weather conditions, while not ideal, were acceptable. The moment that everyone had been working toward for more than 2 years was at hand. On Monday, August 25th, at 10:30 in the morning Pacific Daylight Time, Commander Spike Long climbed into the F-5 SSBD for its first sonic boom flight test. The surface temperature was already 91 degrees Fahrenheit. Long took off at 11:02 and climbed rapidly to altitude. He was joined by Jim Smolka in an F/A-18B for photo chase and Dana Purifoy in an F-15B for the first in-flight probing of the F-5 SSBD's shockwaves. The F-15B had been specially instrumented with a nose boom containing pressure sensors that could measure shockwaves as the aircraft flew through them. NASA Dryden had improved the system since earlier tests, adding sensors capable of 400 samples per second for capturing detailed shockwave signatures. As Long reached 47,000 feet and turned toward the supersonic corridor, Purifoy's F-15B followed closely, positioned to fly through the F-5 SSBD's shockwaves during the high-speed run. Long lit his afterburners and began a 12-degree dive, accelerating through the sound barrier. The tune-up of the engines proved successful. Even in the hot temperatures, the F-5 SSBD reached Mach 1.41 before leveling off at 31,500 feet. It then led the F-15B through the supersonic corridor at Mach 1.38, with the F-15 flying below and slightly behind, its sensitive nose boom measuring the pressure signatures of the shockwaves streaming back from the modified F-5E. The sophisticated GPS tracking system aboard both aircraft worked perfectly, displaying their relative positions to within centimeters. This precision was crucial for correlating the shockwave measurements with the exact positions and flight conditions of the aircraft. When Charles Boccadoro received word that the aircraft had hit its mark, achieving the desired Mach number despite the unfavorable temperatures, he immediately called Steve Walker at DARPA to report the good news. The first flight test had been successful. The aircraft could reach its design speed. The instrumentation was working. They were ready for the main event. The next day, Tuesday, August 26th, thunderstorms in the area forced a postponement. But Wednesday, August 27th, dawned clear and calm. The wait was over. Everything was ready. The morning's flight would answer the question that had driven decades of research. Can an aircraft's sonic boom be shaped to reduce its intensity on the ground? In just a few hours, the world would know. August the 27th, the historic flight. The ground crews arrived at their sensor sites in the darkness before dawn on Wednesday, August 27th, 2003. They navigated the desert roads carefully, watching for the reflectors marking their equipment locations and keeping alert for any desert tortoises that might be crossing the roads. The pre-dawn air was cool and still, perfect conditions for sonic boom measurements. Any turbulence in the lower atmosphere would distort the shockwave signatures, so the calm morning air was exactly what the researchers needed. At the sensor sites scattered along Cords Road and to the north and south, technicians began their final preparations. They checked microphone calibrations, verified that recording systems had sufficient power and storage capacity, and confirmed that all connections were secure. The most sophisticated sensors, the boom amplitude and direction sensor systems developed by NASA Dryden, would activate automatically when they detected the characteristic pressure rise of an incoming shockwave. But the microphone systems required manual activation, time to start recording just before the aircraft began their supersonic runs. At the Northrop Grumman Control Center at Plant 42, Ken Plotkin was examining the latest atmospheric data. Weather balloons had been launched from Edwards and other facilities in the region, measuring temperature, pressure, humidity, and wind conditions throughout the atmosphere from ground level to above 50,000 feet. These measurements were crucial because atmospheric conditions strongly influence how sonic booms propagate. Temperature inversions could focus or defocus shock waves. Strong winds aloft could shift the boom carpet laterally. Turbulence could distort the boom signatures. Plotkin studied the data carefully, looking for any conditions that might compromise the measurements. What he saw was encouraging. There was a slight thermal inversion near the surface, which would actually help by reducing turbulence. Winds aloft were light and steady. Visibility was excellent. While the temperatures at altitude were still warmer than standard, they were acceptable. After conferring with other team members, Plotkin gave the go-ahead for the flight test. At NASA Dryden's control room at Edwards, Peter Cohen and his team prepared to monitor the flight. They had displays showing the planned flight path, weather conditions, and real-time telemetry from the aircraft. They could track the aircraft's positions with GPS precision and monitor critical flight parameters. If anything went wrong, they could advise the pilots immediately. But everyone hoped that the morning's flight would proceed exactly according to plan. At precisely 6:26 local time, just as the sun was beginning to rise above the eastern horizon, Roy Martin in the F-5 SSBD and Lieutenant Commander Dwight "Tricky" Dick in a Navy F-5E took off from the runway at Air Force Plant 42. Both pilots were using the call sign Leahy for their flights. As the two aircraft climbed into the dawn sky, Martin's F-5 SSBD, with its distinctive blue and white pinstriped paint scheme, was clearly identifiable even from the ground. The original plan had called for the standard F-5E to fly first, followed 45 seconds later by the modified F-5 SSBD. This would allow direct comparison of their sonic boom signatures under identical atmospheric conditions. But the arrangement was reversed at the last minute because of concerns that the modified F-5 might have difficulty keeping up with the sleeker baseline aircraft in the higher than normal temperatures. So Martin led the formation, with Dick following. As they climbed to altitude, the pilots compared their altimeter and Mach meter readings to ensure their instruments were synchronized. They needed to fly identical flight profiles at identical speeds and altitudes to make the comparison valid. When they reached 45,000 feet about 20 minutes after takeoff, Dick performed a gradual S maneuver to drop back to the required 45-second spacing behind Martin. The separation had to be precise, too close, and the second aircraft's boom might be affected by the first. Too far and atmospheric conditions might change between the measurements. At 6:44, Martin was cruising at Mach 0.9 over Mojave Airport. He lit his afterburners, hearing and feeling the satisfying rumble as they ignited. He smoothly pushed the stick forward, entering a 12-degree dive while the engines accelerated the aircraft through the sound barrier. The acceleration was rapid. The F-5 SSBD had relatively low drag for a supersonic aircraft, and the tuned engines were producing their maximum rated thrust despite the warm temperatures. Martin watched his Mach meter climb: 1.1, 1.2, 1.3. As he approached Mach 1.4, he began pulling back on the stick to level off. The G-forces pressed him down into his seat as the aircraft transitioned from the dive into level flight at 32,000 feet. His Mach meter stabilized at 1.36, about 920 miles per hour, well within the parameters required for the test. Behind him, Tricky Dick was flying exactly the same profile, matching Martin's speed and altitude. But there was a problem Martin hadn't anticipated. A thick surface haze layer extended up several thousand feet from the desert floor. The combination of the haze and flying directly into the rising sun made it impossible for him to see Cords Road or the other landmarks he was supposed to use for navigation. He had to rely entirely on his handheld GPS unit, watching the small screen to track his position relative to the planned flight path. Flying a jet fighter at nearly 1,000 miles per hour while watching a GPS display takes intense concentration, but Martin had decades of test pilot experience to draw on. 14 miles west of the recording array, Martin settled into steady, level supersonic flight. The aircraft was performing beautifully, holding Mach 1.36 at 32,000 feet, exactly as planned. The ride was smooth. At this altitude, the air was laminar with minimal turbulence. He flew across the sensor array, maintaining precise speed and altitude, then continued east for several more miles before throttling back and slowing to subsonic speed. Behind him, Tricky Dick followed the same flight path, crossing the array 45 seconds after Martin at the same speed and altitude. Two sonic booms, separated by 45 seconds, propagated down through the atmosphere toward the desert floor below. The shock waves from both aircraft travelled downward at the speed of sound, taking about 30 seconds to traverse the 6 miles from the aircraft to the ground. As they travelled, the shock waves evolved, with atmospheric effects slightly modifying their shape and intensity. But the fundamental character of each boom was set by the aircraft's shape. On the ground at the sensor sites, the booms arrived with their characteristic double crack. First Martin's boom from the F-5 SSBD, then Dick's from the standard F-5 E-45 seconds later. To the human ear, there was a noticeable difference. David Graham, working at one of the sensor sites, thought the second boom sounded distinctly louder than the first. But human perception can be subjective. The real question was what the instruments recorded. Data from the sensors began flowing into laptop computers at the sites almost immediately. What the screen showed was stunning. The sonic boom from Dick's standard F-5E displayed the classic N-wave signature that had characterized every supersonic aircraft for the past 56 years. A sharp pressure rise at the bow shock, a gradual decrease to below ambient pressure, and another sharp rise at the tail shock. The initial overpressure measured 1.2 pounds per square foot, typical for an F-5 class aircraft at this altitude and speed. But the signature from Martin's F-5 SSBD was completely different. Instead of the sharp N-wave, it showed a distinctive flat-top shape. The pressure still rose at the leading edge of the signature, but the rise was slower and less abrupt. Then, instead of immediately decreasing, the pressure stayed roughly constant for a period before dropping back down. The initial overpressure was only 0.82 pounds per square foot, 32% lower than the baseline F-5E. This wasn't just a small difference that required statistical analysis to detect. It was obvious, unmistakable, and exactly what the design team had predicted. The blue and red pinstripes painted on the F-5 SSBD's fuselage, representing the flat top and N-wave signatures, had proven to be accurate representations of reality. The aircraft had been designed using computational fluid dynamics to produce a specific shockwave pattern, and that pattern had manifested exactly as predicted when measured on the ground. As the data was transmitted back to the control center at Plant 42, the reaction was immediate and emotional. Ken Plotkin, the sonic boom expert who had spent decades studying this phenomenon, did a small victory dance. This was vindication of theories he had worked on for years. Charles Boccadoro, who had managed the program through all its challenges and setbacks, felt a wave of relief and satisfaction. 2 years of intensive effort had just been validated in less than a minute of supersonic flight. Plotkin immediately called Albert George at Cornell University. George and his colleague Richard Seabass had published the theoretical foundation for sonic boom minimization 32 years earlier, in 1971. Their paper had predicted that aircraft shaping could reduce sonic boom overpressure significantly. But for more than 3 decades, their theory had remained untested. Nobody had built and flown an aircraft designed to generate a shaped boom. Now, in one historic flight, their theory had been proven correct beyond any doubt. When Plotkin told George the news, the professor's response was characteristically understated. "I knew it would." At NASA Dryden's control room, Peter Cohen was equally exuberant. When he saw the flat-top signature displayed on the computer screen, he jumped up from his seat and announced to everyone present that they had just witnessed a classic flat top. The decades of research, the computational tool development, the wind tunnel testing, and all the planning that had gone into this program had just paid off. This wasn't just an incremental improvement or a marginal reduction in boom strength. This was a fundamental change in the character of the sonic boom signature. Back in the air, Martin and Dick were landing at Plant 42, touching down at 7:03 and 7:04 respectively. They taxied back to Northrop Grumman Site 3 and shut down their engines at 7:22. As they climbed out of their aircraft and removed their helmets, they were met by team members eager to show them the data. Both pilots looked at the laptop display showing the two sonic boom signatures overlaid on the same graph. The difference was unmistakable even to someone who wasn't an acoustic specialist. The modified F-5's signature was broader, flatter, and measurably smaller in peak amplitude. The successful flight test answered the most fundamental question. Yes, it was possible to shape a sonic boom through aircraft design. The George Seabass theory was correct. Computational fluid dynamics could accurately predict the sonic boom signature. And most importantly for the future of supersonic aviation, there was now a proven path forward for designing aircraft that could fly supersonic without creating the thunderous booms that had banned such flight over land for 3 decades. But this single flight, as successful as it was just the beginning. The test team wanted more data under different conditions to fully characterize the shaped boom and understand how it behaved in various circumstances. Additional flights were planned for that afternoon and the following days. Each flight would add to the database of measurements, building confidence in the results and providing material for detailed analysis. At 9:05 Pacific Daylight Time, less than 3 hours after the morning's historic flight, the aircraft were ready to fly again. Spike Long climbed into the F-5 SSBD while Tricky Dick prepared the baseline F-5E for another comparison run. They took off and climbed to altitude, following essentially the same profile as the morning flight. This time Long pushed the F-5 SSBD even faster, reaching Mach 1.41 during the dive, before settling into level flight at Mach 1.38. Despite flying about half a mile north of the planned course because of crosswinds, the sensor array recorded both sonic booms satisfactorily. The signatures were consistent with the morning's results, confirming that the shaped boom was repeatable. Another flight the following morning, August 28th, provided more data. Each measurement added confidence that the shaped boom signatures were consistent and real. The test team was accumulating evidence that the acoustic reduction wasn't a fluke of atmospheric conditions, but a genuine consequence of the aircraft's shape. The data collected in these few flights represented the first time in history that anyone had measured shaped sonic boom signatures from an actual aircraft in actual flight conditions in the real atmosphere. All previous sonic boom research had involved conventional aircraft generating N-wave signatures. All the theoretical papers, computational predictions, and wind tunnel tests had been preparing for this moment, and now the moment had arrived, and the reality matched the predictions almost perfectly. On Thursday, August 28th, Northrop Grumman, DARPA and NASA issued a joint press release announcing the previous day's successful demonstration. What had been a rather obscure research program known mainly to specialists in aeronautics suddenly became news. Aviation publications reported the breakthrough. General media outlets picked up the story. Articles appeared in newspapers across the country. CNBC aired video reports showing the modified F-5 and interviews with team members. The shaped sonic boom demonstration had captured public and industry attention. On September 3rd, the principals held a briefing at the National Press Club in Washington, D.C. Representatives from both aviation and general media attended. Charles Boccadoro presented a detailed slideshow on Northrop Grumman's work. He relayed how they first learned of the success, describing the call from the desert, reporting that they could actually hear the difference between the two booms. Richard Wolesian from NASA stated that the results were about as unambiguous as you could get. Peter Cohen noted that while the team was confident the design would work, field measurements of sonic booms are notoriously difficult, so they were all blown away by the clarity of what they measured. The achievement was placed in historical context. As Valesian pointed out, this demonstration was the culmination of 40 years of work by visionary engineers who refused to accept that the sonic boom problem was unsolvable. From the first measurements of sonic booms in the 1960s, through the theoretical breakthroughs of the 70s, the computational advances of the 80s and 90s, and finally to this flight test in 2003, it had been a long journey. But now, finally, there was proof that the sonic boom could be tamed. The timing of the achievement was fortuitous. The Federal Aviation Administration had been reviewing its noise standards, including the regulation that prohibited supersonic flight over land. In May 2003, the FAA had begun seeking comments in advance of a technical workshop. The successful SSBD tests provided concrete evidence that quiet supersonic aircraft might be feasible, giving regulators something concrete to consider rather than just theoretical predictions. In November 2003, the FAA held a civil supersonic aircraft technical workshop in Arlington, Virginia. The aerospace industry used the forum to present their findings and argue that the sonic boom prohibition was the most serious impediment to developing supersonic business jets. Steve Comodina and David Graham from Northrop Grumman discussed the promising results of their SSBD flight tests. Gulfstream, Boeing, and other companies made presentations on addressing sonic boom and jet noise problems. The message was clear. Technology now existed to potentially enable quiet supersonic flight, and the regulatory framework should evolve to accommodate this progress. But even as the success of the SSBD was being celebrated, the participants recognized that much more work remained. The August flights had been limited in number and scope. Only a few sonic boom measurements had been collected, all under relatively favorable conditions. The unfavorable high-altitude temperatures had limited some aspects of the testing. Some instrumentation hadn't worked as well as hoped. There were questions about how the shaped boom would behave under different flight conditions, in turbulent atmospheres, during maneuvers, and at off-design speeds. NASA was particularly interested in gathering more data to validate computational tools and understand atmospheric effects. Peter Cohen began working to secure funding for an extended test program that would conduct approximately 20 more flights in cooler weather when the F-5 SSBD could reliably reach Mach 1.4. These additional tests would be called the Shaped Sonic Boom Experiment to distinguish them from the original DARPA-funded demonstration. But getting approval and funding for this follow-on program would take time. The challenge was that the F-5 SSBD existed on borrowed time. The aircraft belonged to the Navy, which had loaned it for the demonstration program. At some point it would have to be returned. Also, Northrop Grumman's corporate management, having already invested more than $4 million in discretionary funds over a longer period than originally planned, was not eager to continue funding the program indefinitely. If NASA wanted more flights, NASA would need to provide the funding. Fortunately, NASA's Vehicle Systems Division agreed that the additional testing would be valuable and allocated approximately $1 million for a follow-on experiment. The Air Force Research Laboratory would manage the contract with Northrop Grumman through an Air Vehicles Technology Integration Program. The Navy agreed to extend its loan of the aircraft through the end of January 2004. This would provide time for about 20 more flights in the cooler temperatures of winter, when the F-5 SSBD could reach its full performance potential. But that was still several months away. In the meantime, the test team began analyzing the data from the August flights in detail, preparing to present their findings at technical conferences and planning for the follow-on experiment. The ground instrumentation had to be redesigned based on lessons learned. Flight profiles had to be refined. Additional capabilities, including midfield measurements from a glider, had to be integrated into the test plan. All of this preparation would unfold over the fall of 2003, setting the stage for an even more comprehensive test program in January 2004. The August 2003 flights had proven the concept. The January 2004 flights would explore it in depth, generating a rich database of measurements that would validate computational tools, reveal how shaped booms behaved under various conditions, and provide insights that would guide the design of future quiet supersonic aircraft. The breakthrough was real, but the scientific work was just beginning. The Shaped Sonic Boom Experiment, 21 flights in 10 days. Through the fall of 2003, preparations for the follow-on testing proceeded at an intense pace. NASA's Shaped Sonic Boom Experiment Working Group, with essentially the same membership as the SSBD team, met in mid-November in Arlington, Virginia, to establish requirements and review the preliminary test plan. They were determined to extract maximum value from what would likely be their only opportunity to conduct extensive testing with the world's only shaped boom aircraft. The test plan was ambitious: 20 flight tests over approximately 2 weeks in January 2004. These flights would explore the F-5 SSBD's sonic boom characteristics across a range of conditions. Some flights would repeat the basic comparison tests from August, but now in the cooler temperatures where the aircraft could reliably reach Mach 1.4. Other flights would examine off-design conditions, flying at higher or lower speeds and altitudes to see how the shaped boom signature changed. 2 entirely new mission profiles were added, intentionally focusing a boom through a pushover maneuver and having 2 F-5s fly in close formation to measure their booms nearly simultaneously. Based on lessons learned from the August testing, several significant changes were implemented. The sensor array would be relocated to a less remote location within Edwards Air Force Base proper, specifically an area called North Base across Rogers Dry Lake from the main facilities. This would eliminate the long drives to Harper Lake, simplify security arrangements, and make it easier for the ground crews to set up and monitor equipment. The flight path would run from east to west instead of west to east, putting the sun behind the pilots instead of in their eyes during morning flights. Perhaps most innovative was the addition of a sailplane to measure midfield shock waves between the aircraft and the ground. The August testing had planned to use corporate jets for this purpose, but acoustic and mounting complications had forced cancellation of those missions. For the January test, NASA Dryden proposed using a Czech-made Blanik L-23 sailplane from the US Air Force Test Pilot School. This glider was almost perfectly quiet, generating minimal aerodynamic noise that might contaminate measurements. It would be towed to about 10,000 feet, released, and then glide over the sensor array at 6,000 to 8,000 feet, while the F-5s flew supersonic overhead at 32,000 feet. The ground sensor array for the Shaped Sonic Boom experiment was more comprehensive and better instrumented than what had been deployed along Cords Road in August. 26 primary sensor sites, designated Alpha through Zulu, were placed 500 feet apart in a straight line paralleling the North Base runway. Additional sites provided fine-scale sampling and lateral measurements. A total of 42 sensors would record sonic boom data using a variety of measurement techniques. NASA Dryden provided automatic sensing systems at 13 sites. These included the boom amplitude and direction sensor systems from the August tests, plus newly fabricated Bass-O-Matic units and Sabre systems originally designed for mounting on aircraft. NASA Langley and Weil Laboratories provided sophisticated microphone systems at other sites using Bray 1-4L and Kia Type 4-193 low-frequency condenser microphones feeding into advanced recording equipment. Some sites used DAT digital audio tape recorders. Others used laptop computers with special data acquisition cards that allowed immediate viewing of sonic boom signatures as they were recorded. Each sensor location was surveyed using post-processed carrier phase differential GPS to determine its position to within 3 centimeters. This precision was necessary for accurate analysis of the data, as even small errors in sensor positions could affect calculations of shockwave angles and propagation paths. A portable weather station was deployed to monitor surface conditions throughout the testing. The F-15B nose boom probing system was significantly upgraded from the August configuration. The analog differential pressure transducer's sampling rate was more than doubled to 977 samples per second. The reference tank used to calibrate pressure measurements was replaced with a smaller, more carefully sized unit that wouldn't saturate during the aircraft's rapid descent from 45,000 feet to 32,000 feet. These improvements would enable the F-15B to capture much more detailed shockwave signatures during its probing missions. The Blanik sailplane required special instrumentation. A Bra-1 Fortrell and Kier microphone was mounted on the left wingtip with a bullet nose attachment and windscreen to minimize wind noise. Inside the glider, a Sabre unit would automatically record sonic booms when it detected the characteristic pressure signatures. A sophisticated GPS receiver provided position and velocity data. A handheld GPS unit with moving map display helped the pilot navigate to be in the right position when the sonic booms arrived. By early January 2004, all preparations were complete. The F-5 SSBD had been thoroughly inspected and was certified ready for the intensive flight schedule. The ground array had been deployed and tested. The sailplane and its tow plane were ready. The F-15B had been upgraded and checked out. Weather forecasts looked promising for mid-January. The only problem was that Commander Spike Long, who had flown several of the August missions and was scheduled to alternate with Roy Martin as the SSBD pilot, came down with a stubborn head cold just before testing was to begin. He had to remove himself from flight status for the entire program. This meant Roy Martin would fly all 21 SSBE missions himself, a grueling schedule of almost daily flights for 2 weeks. The testing began on Monday morning, January 12, 2004. Martin took off at 9:45 in the morning for what was essentially a functional check flight, though it included an attempt at Schlieren photography and a practice run creating a focused boom through a pushover maneuver. The F-18 chase plane tried to photograph the F-5 SSBD's shockwaves during the supersonic pass, while the Blanik glider positioned itself below to measure the sonic boom. Everything worked well, confirming that the team was ready for the full test program. The ambitious schedule called for 3 flights on January 13th. Martin and Lieutenant Commander Tricky Dick, flying the baseline F-5E that had deployed from Fallon, conducted back-to-back sonic boom comparison runs on all 3 missions. They flew the profile that had proven so successful in August, climbing to 45,000 feet, then diving to accelerate through the sound barrier, leveling off at 32,000 feet at Mach 1.4, and flying across the ground array with the standard F-5E following 45 seconds behind. Each mission followed a similar pattern, but wasn't without complications. On the first flight, Martin's GPS telemetry malfunctioned and stopped transmitting data to the ground station. The Ashtec Z12 GPS unit was rebooted before the next flight, and the problem seemed to be solved. But then Dick's F-5E experienced the same telemetry failure. Its GPS had to be reprogrammed as well. These glitches were frustrating, but didn't prevent the missions from collecting good data. The GPS units continued to record internally even when their telemetry failed, so the data could be downloaded after landing. On January 14th, Martin and Dick flew 2 more comparison missions at off-design speeds. The first was at Mach 1.43, slightly faster than the design condition. The second was at Mach 1.35, slower than design. These flights would reveal how sensitive the shaped boom signature was to speed variations. Did the flat-top signature persist at different Mach numbers, or did it revert to a conventional N wave when the aircraft flew away from its design point? January 15th brought 3 more flights with the baseline F-5E, including the final mission before it returned to Fallon. The morning included 2 more off-design speed missions, one at Mach 1.43 and one at Mach 1.35. The afternoon featured an entirely different mission profile, the close-behind formation flight. The idea was to have both F-5s fly through the sensor array nearly simultaneously, with the baseline F-5E positioned just 580 feet behind and 19 degrees below the F-5 SSBD. This would subject both sonic boom signatures to identical turbulence conditions, allowing researchers to determine how much of any signature distortion was caused by atmospheric effects versus aircraft characteristics. Unfortunately, this mission didn't work quite as planned. The baseline F-5E, with its centerline pylon still attached from the ferry flight, couldn't keep up with the F-5 SSBD during the supersonic acceleration. It fell progressively farther behind, crossing the sensor array 2 seconds after the modified aircraft, instead of nearly simultaneously. The ground measurements were still useful, but they couldn't provide the direct turbulence comparison the researchers had hoped for. With the baseline F-5E having returned to Fallon, the remaining 15 flights would be solo missions by the F-5 SSBD. On January 16th, Martin flew one afternoon sortie at Mach 1.35. January 17th brought 3 morning flights exploring off-design conditions. The first was a pushover maneuver to create a focused boom. The second and third flew at 36,000 feet instead of the usual 32,000, one at Mach 1.375 and one at Mach 1.45, the highest speed permitted by the Navy flight clearance. The focused boom flights were particularly interesting from a research standpoint. When an aircraft accelerates, turns, or begins to descend with a pushover maneuver, the shock waves can focus at a point on the ground, creating a much stronger boom than the steady cruise boom. These focused or super booms were inevitable for any supersonic aircraft during certain phases of flight. The question was whether a shaped boom aircraft would create less intense focused booms than a conventional aircraft. On January 17th, Martin performed a 0.5 G pushover for 3 seconds, focusing a boom toward the sensor array. The measurements would reveal the focused boom signature from a shaped boom aircraft for the first time. January 19th brought 3 more solo flights. The first included another focused boom attempt with a 0.1 G pushover. The next 2 flights introduced a new profile: dual direction passes. Martin would make one supersonic pass from east to west over the sensor array, then make a tight supersonic turn and come back west to east for a second pass. This doubled the data collection from each flight. Even with the extra afterburner time needed for 2 supersonic runs, the F-5 SSBD landed with over 1,000 pounds of fuel remaining, demonstrating that the profile was sustainable. The final 2 days of testing, January 21st and 22nd, were devoted to near-field probing by the F-15B. Dana Purifoy, with either Mike Thompson, Craig Bombin, or Frank Bateas in the back seat, flew the instrumented F-15B on 4 missions. Martin would take off in the F-5 SSBD, rendezvous with the F-15B at altitude, and lead it through supersonic runs while the F-15 slid below and behind to fly through the shockwaves. The probing procedure required exceptional flying skill and coordination. The 2 aircraft would fly side by side until Martin initiated his supersonic acceleration. Purifoy would then position his F-15 slightly below and behind, watching Martin's aircraft while simultaneously trying to keep a vector symbol in his heads-up display on the horizon to maintain precisely level flight. When Martin radioed that he had reached the target Mach number, Purifoy would gently push his throttles forward to increase speed just enough to slowly move through the F-5 SSBD's shockwave pattern. The F-15's pressure transducers could detect shockwaves as small pressure disturbances, but Purifoy and his backseaters could also feel them. The shockwaves would buffet the aircraft slightly as it passed through them. The backseater would call out instrument readings since the shockwaves disrupted the F-15's air data system. Meanwhile, engineers in the Dryden control room watched real-time displays of both aircraft's positions and the nose boom pressure measurements. When they saw that the F-15 had passed through the bow shock, they would tell Purifoy to slow down and back out. Then the two aircraft would set up for another probe. On the dual direction missions, Martin and Purifoy would conduct multiple probes on the eastbound pass, make a tight turn while staying supersonic, and then conduct more probes on the westbound pass. The precision required was remarkable. The F-15 had to fly within a few hundred feet of the F-5 SSBD, below and behind it, while both aircraft were traveling at nearly 1,000 miles per hour. Any significant deviation in position would compromise the measurements. Any abrupt control inputs by either pilot could create unwanted disturbances. Over the 4 probing missions on January 21st and 22nd, Purifoy completed 68 successful near-field probes at various distances and lateral positions relative to the F-5 SSBD. Most probes were directly below at about 100 feet distance, but some were made off to the side. Each probe captured a detailed pressure signature showing the shockwave pattern close to the aircraft before the waves had time to coalesce. These near-field signatures would be invaluable for validating computational fluid dynamics codes and understanding exactly how the modifications change the aircraft's shockwave field. On January 22nd, after the final probing flight landed, the intensive test program was complete. In just 11 days, Roy Martin had flown 21 flights in the F-5 SSBD. The ground array had recorded over 1,300 sonic boom measurements. The Blanick glider had captured 29 midfield signatures, plus numerous secondary booms reflected off the ground. The F-15B had collected 68 near-field shockwave probes. All of this was supplemented by extensive atmospheric measurements from weather balloons, surface weather stations, and the GPS-equipped Rowan-Son systems that provided 3-dimensional wind profiles. The testing had been extraordinarily successful by any measure. Nearly perfect weather conditions throughout the period, combined with the excellent reliability of all the aircraft and ground systems, allowed the team to complete their full test plan. Historical weather statistics for Edwards in January had suggested that only early morning flights would meet the atmospheric criteria for good sonic boom measurements, but conditions turned out to be favourable through much of most days. There had been challenges, of course. The GPS telemetry glitches had caused some anxious moments. The close behind formation flight didn't work as planned because of the extra drag from the F-5E's centerline pylon. Some flights had to navigate around turbulence at certain altitudes, but these were minor issues in the context of the overall success. The test team had gathered an unprecedented database of shaped sonic boom measurements under a wide variety of conditions. Now came the next phase, getting the F-5 SSBD back to Florida and eventually returning it to the Navy. Roy Martin flew the aircraft out of Palmdale on January 23rd, but the ferry flight didn't go smoothly. On the third leg, the FA-18 escort from Naval Air Station China Lake had an in-flight emergency and had to divert to Memphis. Martin continued to Birmingham, Alabama, where he was stranded for 3 nights waiting for weather to clear in northern Florida and for another escort aircraft to arrive. Finally, on January 27th, accompanied by a Northrop Grumman Citation business jet, he flew the Pelican back to St. Johns County Airport, where its journey had begun 6 months earlier. The aircraft was disassembled in August 2004 and delivered to the Valiant Air Command Museum in Titusville, Florida. Rather than being scrapped for parts as originally planned, the Navy had recognized the historical significance of this unique aircraft and agreed to have it preserved. After being reassembled and restored by museum volunteers, the Pelican went on display in June 2006, where it remains today as a testament to the breakthrough it achieved. Analyzing the data. What the numbers revealed. With the shaped sonic boom experiment flights complete, the real work of analyzing the vast quantity of data began. The team had collected over 1,300 ground-based sonic boom measurements, 29 midfield measurements from the sailplane, 68 near-field shockwave probes from the F-15B, and extensive atmospheric data. All of this information had to be carefully processed, cross-checked, correlated, and analyzed to extract meaningful insights about shaped sonic boom characteristics. The data analysis effort involved researchers from NASA Langley, NASA Dryden, Northrop Grumman, Weil Laboratories, Eagle Aeronautics, Gulfstream, Boeing, and Lockheed Martin. They worked through the spring and summer of 2004, preparing preliminary results for presentation at an SSBE closeout workshop held at NASA Langley on August 17th. The analysis would continue for months beyond that, eventually resulting in more than a dozen peer-reviewed technical papers presented at aerospace conferences and published in technical journals. The most fundamental question was whether the shaped boom signatures measured on the ground matched computational predictions. The answer was a resounding yes. The flat-top signatures recorded during the SSBD and SSBE were remarkably consistent with what the computational fluid dynamics analyses had predicted. The pressure rise at the leading edge was slower and less abrupt than an N wave. The signature showed a plateau region where pressure remained relatively constant. The peak overpressure was consistently lower than the baseline F-5E by approximately 30 to 35%. This agreement between prediction and measurement was enormously significant. It meant that the computational tools used to design the F-5 SSBD modifications were accurate and reliable. Engineers could use these same tools with confidence to design future-shaped boom aircraft, knowing that if the computer simulations predicted a certain signature, the actual aircraft would produce that signature. This validation of the design tools was perhaps as important as demonstrating the shaped boom itself. The consistency of the shaped boom signatures across multiple flights and various conditions was also noteworthy. Whether the F-5 SSBD flew at 6:30 in the morning or at 2 in the afternoon, whether it flew at Mach 1.35 or Mach 1.45, whether surface winds were calm or gusty, the basic character of the shaped boom persisted. The plateau signature was robust. It didn't disappear in less than perfect conditions. This robustness was crucial for any practical application. A shaped boom that only worked under ideal laboratory conditions wouldn't be useful for an operational aircraft. One of NASA's primary objectives in funding the SSBE was to understand how atmospheric turbulence affected shaped boom signatures. Turbulence was known to distort conventional N-wave signatures, roughening the shock fronts and sometimes altering the perceived loudness. Would shaped booms be even more sensitive to turbulence, potentially losing their acoustic benefits in typical atmospheric conditions? The January testing deliberately included flights later in the day when surface heating would generate more turbulence, and the sailplane measurements provided crucial data for understanding turbulence effects. Ken Plotkin, Ed Herring, Dominic Maglieri, Brenda Sullivan, and Joseph Salamoni analyzed the sailplane data in detail. They compared boom signatures measured by the sailplane in relatively smooth air at 6,000 to 8,000 feet with signatures measured on the ground, where surface turbulence was stronger. What they found was encouraging. While turbulence did distort the signatures, adding ripples and irregularities to the plateau region, it didn't destroy the basic flat-top character. The shaped boom remained recognizably shaped, and more importantly, it remained quieter than a conventional boom, even in turbulent conditions. The researchers developed a turbulence subtraction algorithm that could remove the effects of turbulence from ground measurements, revealing what the signatures would have been in a standard atmosphere with no turbulence. The technique exploited the fact that turbulence affects the front and rear shocks of a boom signature in similar ways. By analyzing the distortion pattern on the rear shock, which was simpler in structure, they could create a template to subtract turbulence effects from the more complex front shock. This method successfully cleaned up signatures, revealing smooth, flat-top shapes beneath the turbulent noise. The acoustic analysis conducted by Brenda Sullivan revealed that the shaped boom was even quieter than its reduced peak overpressure would suggest. The reduction in overpressure from 1.2 pounds per square foot for the baseline, F-5E to 0.9 pounds per square foot for the F-5, SSBD should have corresponded to about 2.5 decibels of noise reduction. But acoustic analysis of 132 booms recorded by 19 microphones showed the shaped boom averaged 4.7 decibels quieter. This additional acoustic benefit came from the slower rise time of the shaped boom. Spreading the pressure change over a longer time period reduced not just the peak pressure, but also the high-frequency acoustic content, making the boom sound less sharp and startling. The focused boom flights provided unexpected insights. When Martin performed pushover maneuvers to create focused booms, the sensors recorded strong U-wave signatures with peak overpressures approaching 3 pounds per square foot, as predicted. But an unexpected finding was that the post-focus boom carpet, after the focused region passed, showed conventional N-wave signatures rather than flat tops. Analysis revealed why. During the pushover maneuver, the aircraft was flying at low lift coefficient and high dive angle, an off-design condition where the shaping wasn't optimized. This finding was actually useful, suggesting that focused booms from shaped aircraft might be less intense than from conventional aircraft because the off-design condition produced a more complex wave pattern that didn't focus as effectively. The near-field probing data from the F-15B flights was crucial for validating computational fluid dynamics at the most fundamental level. These measurements showed the shockwave patterns mere tens or hundreds of feet from the F-5 SSBD before the waves had coalesced. The data revealed multiple distinct shocks from the nose, wing leading edges, engine inlets, and aft fuselage. The measurements could be directly compared with CFD predictions of the near-field pressure signatures, and the agreement was excellent. Keith Meredith at Northrop Grumman led the computational validation effort. He selected 6 of the 68 probes based on data quality and flight conditions, then ran high-fidelity CFD simulations of those exact flight conditions. The CFD code solved the Reynolds averaged Navier-Stokes equations on grids with more than 14 million points, capturing the complex three-dimensional flow around the aircraft with remarkable detail. The simulated shockwave signatures matched the flight measurements with impressive accuracy, further validating the computational tools. The CFD visualizations provided stunning insights into how the modifications changed the F-5's shockwave field. Compared to a standard F-5E, the F-5 SSBD had a stronger bow shock closer to the nose. But this strong near-field shock prevented downstream shocks from moving forward and coalescing with it. The underbody fairings created an expansion region that reduced the engine inlet shock. The overall effect was a shockwave pattern that, when propagated to the ground, produced the desired flat-top signature. Data from the close-behind formation flight, while not providing the turbulence comparison originally intended, did yield interesting results. Even though the two aircraft were separated by 2 seconds instead of being nearly simultaneous, the comparison showed that surface turbulence was indeed affecting both signatures similarly. Both booms showed similar distortion patterns from turbulence, confirming that the measurement techniques were working properly and that turbulence effects could be analysed systematically. The off-design flights at various speeds and altitudes revealed how sensitive the shaped boom signature was to flight conditions. At speeds close to the Mach 1.4 design point, the flat-top character persisted well. At Mach 1.35 and Mach 1.43, the signatures were still clearly shaped, though with some differences in the plateau height and duration. At Mach 1.45 and 36,000 feet, the highest speed mission, the signature showed some degradation but remained fundamentally different from an N wave. These findings suggested that a shaped boom aircraft would maintain beneficial sonic boom characteristics across a range of cruise conditions, not just at one narrow design point. This was important for practical applications. A supersonic business jet, for example, would need to fly at various speeds and altitudes depending on winds, air traffic control requirements, and fuel optimization. The fact that shaped boom characteristics persisted across a reasonable flight envelope was encouraging. All of this analysis led to a comprehensive understanding of the physics and practical characteristics of shaped sonic booms. The George Seabass theory was correct. Computational fluid dynamics could accurately predict sonic boom signatures. Aircraft shaping could reduce sonic boom perceived loudness by significant margins, potentially by a third or more. The shaped boom was robust to atmospheric variability, and the design methods were validated and ready to be applied to future aircraft. The achievement represented a milestone in aeronautics. After decades of research, sonic boom shaping had been demonstrated in flight. The data collected would support years of additional research and would inform the design of future quiet supersonic aircraft. And the breakthrough would eventually contribute to changing the regulatory environment that had stifled supersonic aviation for 3 decades. Legacy and the future. From the Pelican to the X-59, the shaped sonic boom demonstration and experiment didn't immediately change aviation. There were no announcements of new supersonic airliners in development. Regulations prohibiting supersonic flight over land remained in force. Sonic booms continued to be banned from populated areas, but the project's impact was profound in ways that would gradually become apparent over the following years. The validation of computational design tools was perhaps the most immediate and tangible benefit. Before the SSBD, computational fluid dynamics predictions of sonic boom signatures were treated with skepticism. The tools had been validated against limited wind tunnel data and a few in-flight measurements of conventional booms, but nobody had used CFD to design an actual shaped boom aircraft and then proven that the design worked. Now they had. This validation gave aerospace companies and research organizations confidence to invest in more ambitious shaped boom research programs. The project also demonstrated that shaped boom technology was practical and achievable. The modifications to the F-5E, while extensive, weren't exotic or impossibly complex. They used conventional materials and manufacturing methods. The aircraft handled well and was safe to fly. This practicality was important. If shaped boom aircraft required revolutionary new technologies or manufacturing techniques that couldn't be scaled to production, the concept would remain academic. But the SSBD showed that shaped booms could be achieved with evolutionary improvements to conventional supersonic aircraft design. The data collected during the SSBD and SSBE provided a treasure trove of information for researchers. Over the following years, analysis of that data would result in dozens of technical papers presented at conferences and published in journals. The measurements were used to refine computational models, improve boom propagation prediction methods, and understand atmospheric effects on sonic booms. The database became a standard reference point for sonic boom research worldwide. The success influenced government policy and research programs. The Federal Aviation Administration's awareness that quiet supersonic flight might be feasible began influencing their long-term planning. While they couldn't immediately change regulations, they could start thinking about what standards would be needed for quiet supersonic aircraft. What noise level would be acceptable? How should it be measured? What certification requirements would ensure that aircraft met the standards consistently? NASA's interest in supersonic research was reinvigorated by the SSBD success. The agency had maintained a modest supersonic research program through the 1980s and 90s, but the SSBD demonstration provided justification for expanding those efforts. Peter Cohen and others at NASA Langley began developing plans for a new low-boom flight demonstrator that would be designed from the ground up as a quiet supersonic aircraft, rather than being a modification of an existing design. Industry interest in supersonic business jets also grew. Gulfstream Aerospace had been studying supersonic concepts for years. The SSBD results gave them more confidence that a quiet supersonic business jet was technically feasible. They intensified their research efforts, conducting extensive computational studies and wind tunnel tests of low-boom designs. Other companies, including Ariane Corporation and Spike Aerospace, announced plans to develop supersonic business jets, citing the progress in boom reduction technology as a key enabling factor. Lockheed Martin, building on its participation in the SSBD working group and the computational expertise gained through that program, became particularly active in shaped boom research. The company conducted extensive studies of low-boom configurations, developing increasingly sophisticated designs that could minimize sonic booms while maintaining good aerodynamic efficiency. They built on the fundamental design principles demonstrated by the F-5 SSBD, but explored how those principles could be applied to larger, more practical aircraft designs. The awards and recognition given to the SSBD team reflected the aerospace community's appreciation of the achievement. Aviation Week and Space Technology bestowed one of its prestigious Laurels Awards for 2003 on Charles Boccadoro, Richard Blesian, and Stephen Walker. The American Institute of Aeronautics and Astronautics gave its Aircraft Design Award for 2004 to Charles Boccadoro, Joseph Pawlowski, and David Graham. NASA recognized the entire SSBD team with a Turning Goals into Reality Partnership Award. Roy Martin was inducted as a Fellow of the Society of Experimental Test Pilots. These honors acknowledged not just the technical achievement, but the exemplary collaboration between government, industry, and research organizations that made it possible. The project also demonstrated the value of the working group model for managing complex aerospace research programs. The SSBD working group brought together expertise from multiple organizations, coordinated their efforts, resolved technical challenges through collaborative problem solving, and ultimately delivered a successful program. This model would be used in subsequent NASA aeronautics research programs, proving that government-industry partnerships could be effective when properly structured and managed. Perhaps the most significant long-term impact was on NASA's plans for a new X-plane. In the years following the SSBD, NASA began developing plans for what would eventually become the X-59 Quiet Supersonic Technology Aircraft, or X-59 QuIS-ST. This aircraft would take the lessons learned from the SSBD and apply them to a purpose-built demonstrator designed to produce an even quieter sonic boom, one that might be acceptable for routine overland supersonic flight. The X-59 program began taking shape in the early 2010s. NASA worked with industry partners to conduct extensive design studies, exploring various configurations and assessing their low boom potential. The computational tools validated by the SSBD program were essential to this effort, allowing engineers to predict with confidence how various designs would perform. By 2012, NASA had selected a preliminary design and was moving toward the detailed design and fabrication phase. Lockheed Martin's Skunk Works was eventually selected to build the X-59. The aircraft they designed was dramatically different from the F-5 SSBD in configuration, but followed the same fundamental principles. It had an extremely long, slender nose that comprised nearly a third of the aircraft's total length. The nose was so long that the pilot couldn't see forward over it during landing, requiring a sophisticated vision system. The aircraft had a carefully sculpted shape that distributed volume smoothly from nose to tail. It featured complex underbody shaping to control the shockwave pattern. The design process for the X-59 leveraged everything learned from the SSBD program. The computational tools, refined and validated through analysis of SSBD data, were used to optimize every aspect of the aircraft's shape. The understanding of atmospheric effects gained from the SSBE ground and airborne measurements informed predictions of how the X-59's boom would propagate to the ground. The experience of instrumenting and flight testing the F-5 SSBD guided plans for the X-59 flight test program. Construction of the X-59 proceeded through the late 2010s and early 2020s. The aircraft was assembled at Lockheed's Skunk Works facility in Palmdale, the same area where the F-5 SSBD had been based for its flight tests 20 years earlier. The X-59 was designed to cruise at Mach 1.4 at 55,000 feet, generating a sonic boom with a peak overpressure of about 0.4 pounds per square foot. If successful, this would be about a quarter of the boom from a conventional supersonic aircraft and would sound more like a soft thump than a sharp bang. The X-59 rolled out in January 2024 and began ground testing. First flight is planned for the mid-2020s, followed by an extensive flight test program. Unlike the SSBD, which conducted about 30 flights over a few months, the X-59 is expected to fly for several years, conducting community response tests over various cities across the United States. The goal is to gather data on how people actually react to the quiet sonic boom, providing the information the FAA needs to potentially revise regulations. This is where the story comes full circle. The SSBD proved that shaped sonic booms were possible. The computational tools were validated. The physics was understood. But the question remained, would a shaped boom be acceptable to the public? Would people tolerate flying over their homes and communities if the boom was reduced from a thunderclap to a soft rumble? The X-59 program is designed to answer that question definitively. If the X-59 demonstrates that low sonic booms are acceptable to communities, it could pave the way for regulatory changes that would enable a new generation of supersonic aircraft. The FAA has indicated that it would consider revising Part 91 of the Code of Federal Regulations if sufficient data shows that quiet supersonic flight is feasible and acceptable. Such a change would be momentous. It would end a 50-year prohibition on overland supersonic flight and could enable supersonic business jets, military transports, and perhaps eventually larger commercial supersonic transports. Several companies are positioning themselves to take advantage of such regulatory changes. Boom Supersonic is developing Overture, a 50 to 80 passenger supersonic airliner. While their initial aircraft won't be quiet enough for overland flight, they're incorporating lessons from low boom research into their design process. Lockheed Martin has conceptual designs for quiet supersonic business jets and regional transports. NASA continues to refund advanced supersonic concepts through research programs. The dream of practical, routine supersonic flight over land, which seemed dead after the cancellation of the American SST program in 1971 and the retirement of Concorde in 2003, has been revived. And that revival traces directly back to those flights over Edwards Air Force Base in August 2003 and January 2004, when the F-5 SSBD proved that shaped sonic booms weren't just theoretical predictions but achievable reality. Roy Martin, who flew all but a few of those historic flights, continued his career as a test pilot and consultant. He became a Fellow of the Society of Experimental Test Pilots and served as its president. He accumulated more than 10,000 flight hours in 70 different aircraft types over a career spanning 4 decades. Looking back on the SSBD program years later, he emphasized how the project demonstrated what could be achieved when talented people from different organizations worked together toward a common goal. Charles Boccadoro, the program manager who kept the SSBD on track through all its challenges, went on to other leadership positions at Northrop Grumman. He emphasized that the program succeeded because the team never gave up, even when facing setbacks and unexpected problems. When the weather was too hot, they tuned the engines. When GPS systems malfunctioned, they rebooted and kept flying. When delays threatened the schedule, they worked longer hours to catch up. Persistence and determination made the difference between success and failure. David Graham and the other aerodynamicists who designed the modifications could take satisfaction in seeing their computational predictions validated so convincingly by flight tests. After decades of development, CFD had matured to the point where it could be used with confidence for breakthrough aircraft designs. The success would encourage continued investment in computational tools and methods. Ed Herring, Ken Plotkin, Dominic Maglieri, and the other specialists in sonic boom measurements and analysis extracted years' worth of research material from the data collected. Their papers and presentations educated a new generation of aerospace engineers about sonic boom physics and measurement techniques. The knowledge they generated continues to inform research programs around the world. The F-5 SSBD itself, after being retired and donated to the Valiant Air Command Museum, stands as a physical testament to the breakthrough. Museum visitors can see the dramatically extended nose, the carefully sculpted underbody fairings, and the distinctive blue and white pinstripes representing the N-wave and flat-top signatures. It serves as an educational artifact, explaining the physics of sonic booms and the engineering challenge of reducing them. Looking to the future, supersonic aviation seems poised for a renaissance after decades of stagnation. The technical barriers have been largely overcome. Shaped boom designs are well understood. Computational tools are mature and validated. Manufacturing technologies can produce the complex shapes required. What remains is to demonstrate public acceptance and work through the regulatory process. If that can be accomplished, we may see the 2030s and 40s become an era of practical supersonic travel, with business jets, regional transports, and perhaps transatlantic airliners flying faster than sound over land without disturbing the people below. When that happens, when someone books a 3-hour supersonic flight from New York to Los Angeles and arrives home in time for dinner, when supersonic point-to-point travel becomes routine rather than exotic, they'll have the team that created the shaped sonic boom demonstrator to thank. That modified F-5E, with its pelican-like nose and pinstriped fuselage, will be recognized as the aircraft that proved the concept, validated the tools, and demonstrated that sonic booms could be tamed. Conclusion: the sound of progress. We've journeyed through more than 75 years of aviation history, from Chuck Yeager's barrier-breaking flight in 1947 to the cutting-edge X-59 under development today. We've explored the physics of sonic booms, the regulatory barriers they created, the decades of theoretical research that suggested solutions, and finally the flight tests that proved those solutions worked. The story of the shaped sonic boom demonstration is one of persistence, collaboration, and the refusal to accept that some problems are simply unsolvable. The breakthrough achieved on that August morning in 2003 wasn't just a technical accomplishment. It was a vindication of decades of research by scientists and engineers who believed that supersonic flight's promise shouldn't be limited by the sonic boom. It was proof that computational tools had matured to the point where they could guide breakthrough aircraft designs. It was a demonstration that government, industry, and academia could work together effectively to solve challenging problems. And it was a glimpse of a future where supersonic travel might be routine rather than rare. As we look ahead to the X-59's flights and the possibility of new regulations that could enable quiet supersonic flight over land, we can appreciate how far we've come. The F-5 SSBD's flights were just 30 flights totaling a few dozen hours in the air, but their impact continues to reverberate through the aerospace community. The data collected informs ongoing research. The lessons learned guide current programs. The breakthrough achieved open doors that had been closed for decades. If you've enjoyed learning about the shaped sonic boom demonstration and the quest to quiet supersonic flight, please consider liking this video and subscribing to the channel. There are many more stories of aerospace innovation, breakthrough technologies, and the dedicated people who make them possible. From the X-planes that pushed the boundaries of speed and altitude to the spacecraft that took humanity to the moon and beyond, the history of aerospace is filled with moments of inspiration and achievement. The shaped sonic boom story reminds us that major breakthroughs often take decades of patient work. The theoretical foundation was laid in the 1970s. Computational tools were developed and refined through the 80s and 90s. The flight demonstration came in the early 2000s. And the practical implementation with aircraft like the X-59 is happening in the 2020s. This long timeline reflects the complexity of aerospace development, but also the persistence of those who refuse to give up on important goals. It also reminds us of the importance of fundamental research. When Albert George and Richard Seabass published their sonic boom minimization theory in 1971, there was no immediate application. No aircraft company was clamoring for their results. No government agency had a program waiting to apply their insights. Yet their work, supported by NASA and university research programs, laid the foundation for everything that followed. Without that theoretical groundwork, the SSBD wouldn't have been possible. The collaboration between organizations was equally crucial. DARPA provided initial funding and vision. NASA contributed technical expertise and flight test support. The Navy loaned the aircraft. Northrop Grumman designed and executed the modifications. Weil Laboratories, Eagle Aeronautics, Gulfstream, Boeing, and Lockheed Martin contributed specialized knowledge. No single organization could have accomplished the SSBD alone. It took a team. And ultimately, it took skilled professionals willing to push the boundaries of their fields. Test pilots who flew untested configurations. Engineers who designed unprecedented modifications. Technicians who fabricated parts with exacting precision. Researchers who developed new measurement techniques. Analysts who extracted insights from vast data sets. Every one of them played a crucial role in the success. As supersonic aviation enters what might be its second golden age, enabled by the work done on programs like the SSBD, we can look forward to a future where speed and quiet flight are no longer mutually exclusive. Where supersonic travel is accessible not just to wealthy passengers on transoceanic flights, but to business travelers covering domestic routes, where military aircraft can operate with less environmental disturbance, where the promise of supersonic flight, held back for so many years by the sonic boom problem, can finally be fully realized. The story of the shaped sonic boom demonstration is ultimately a story of hope and possibility. It shows us that with persistence, collaboration, and ingenuity, even problems that have stymied progress for decades can be solved. It reminds us that the challenges we face today in aerospace and other fields are not insurmountable, and it inspires us to keep working toward breakthroughs, knowing that patient effort eventually pays off. Thank you for joining me on this deep dive into one of the most significant but underappreciated achievements in modern aerospace. The quiet thunder generated by the F-5 SSBD over Edwards Air Force Base in August 2003 might not have made headlines like the breaking of the sound barrier did in 1947, but it was no less important. It proved that we could tame the boom, control the shock, and quiet the thunder of supersonic flight. And in doing so, it may have opened the door to a future where supersonic travel is as commonplace as jet travel is today. The sound of progress is sometimes a whisper rather than a roar, and the shaped sonic boom might just be the whisper that changes aviation history.